Welcome back to Scientific Discovery Hub, the channel where we dive into the mind-bending mysteries that shape our universe. Today we're tackling one of the most confounding puzzles in modern physics, the black hole information paradox. Imagine a cosmic vault so secure that not even light can escape. Yet scientists are locked in a battle over whether the data trapped inside is truly lost forever. This isn't just a riddle about black holes. It's a gateway to unlocking the secrets of quantum gravity, the holy grail of theoretical physics. Here's the setup. Black holes have an event horizon, a point of no return where space-time bends so drastically that nothing, not even information, can flee. But this clashes with a cornerstone of quantum mechanics. Information can never be destroyed. Enter Stephen Hawking, whose groundbreaking discovery in 1974 revealed that black holes slowly evaporate, emitting radiation that carries no memory of what fell in. If a black hole vanishes, where does its swallowed data go? This is the heart of the paradox, and solving it could bridge Einstein's general relativity with quantum theory. In this video, we'll unpack the wild ideas physicists have proposed to resolve this cosmic conundrum. We'll explore Hawking radiation, the strange dance of quantum entanglement, and the shocking no-cloning theorem that forbids copying quantum information. Could a firewall of pure energy at the event horizon save the day, or shatter our understanding of gravity? What if black holes are actually wormholes stitching together space-time, or portals to parallel universes in a vast multiverse? We'll also delve into the holographic principle, which suggests our 3D universe is a projection from a 2D hologram, and loop quantum gravity, which reimagines space-time as a woven fabric of discrete loops. This isn't just abstract theory, it's a journey to redefine reality itself. Could information be the fundamental building block of the cosmos, with black holes acting as cosmic hard drives? And what role does consciousness play in observing this quantum dance? By the end, you'll see why the black hole information paradox isn't just a puzzle, it's a Rosetta Stone for unifying physics. If you're ready to explore the edge of knowledge, hit play and join us as we unravel this cosmic enigma. Don't forget to like, subscribe, and ring the bell for more deep dives into the wonders of science. The universe is full of mysteries, and together, we're here to decode them. Let's begin. Imagine standing at the edge of an abyss so profound that it defies comprehension, a chasm where the fabric of space-time itself unravels. This is the event horizon of a black hole, a boundary so absolute that it renders the familiar laws of physics obsolete. To cross it is to surrender to a fate sealed by the very geometry of the universe, a point of no return where even the most fundamental forces of nature, time and space, conspire to erase existence itself. It is not merely a barrier, it is a cosmic gatekeeper, a veil between the known and the unknowable. Beyond this horizon lies a realm where the rules we cling to for understanding the cosmos dissolve into enigma, and the universe reveals its most unfathomable secrets. The event horizon is a paradox in motion, a place where the infinite density of a singularity begins to exert its dominion over the surrounding space. As you approach this invisible line, the gravitational pull grows so intense that it warps the very concept of distance and direction. Light, the fastest traveler in the universe, cannot escape its grasp, rendering the horizon a perfect shadow against the cosmic backdrop. Yet, it is not a wall but a threshold, a moment in time, a decision point where the trajectory of matter, energy, and even information becomes irrevocably bound to the singularity. For an observer outside the horizon, the approach of an object appears to slow to a crawl, frozen in a timeless limbo as the gravitational redshift stretches its form into obscurity. But for the object itself, the descent is swift and unrelenting, a plunge into a void where the known universe ceases to exist. This phenomenon has captivated the imagination of humanity for centuries, evoking awe and trepidation in equal measure. Early thinkers, from ancient philosophers to modern physicists, have grappled with the implications of such a boundary, where the finite and the infinite collide. The event horizon is not just a scientific curiosity, it is a mirror reflecting the limits of human knowledge. It challenges us to confront the possibility that the universe may harbor truths beyond our ability to perceive or comprehend. In its quiet, unyielding presence, The event horizon whispers of a reality far stranger than we dare to imagine, a reminder that the cosmos is as much a riddle as it is a marvel. As we stand on the precipice of understanding this cosmic threshold, we are left with a question that echoes through the ages. What lies beyond the event horizon? Is it the end of all things, or a gateway to something entirely new? The answers, if they exist, lie buried within the folds of space-time, waiting to be unearthed by those bold enough to venture into the unknown. At the heart of the event horizon lies a fundamental truth of the universe. The speed of light is not merely the fastest known entity, but also the ultimate limit imposed by the laws of physics. According to Einstein's theory of general relativity, gravity is not a force acting across space, but a curvature of space-time itself. In the vicinity of a black hole, this curvature becomes so extreme that the escape velocity, the speed required to break free from a gravitational field, surpasses the speed of light. Light, the universe's swiftest courier, is thus ensnared, unable to carry information or energy beyond the event horizon. This boundary marks the point at which the gravitational pull of the black hole becomes absolute, rendering the classical concepts of causality and locality meaningless. To visualize this, consider the event horizon as a one-way membrane. From an external perspective, an object falling toward a black hole appears to decelerate as it approaches the horizon, its emitted light redshifting to longer wavelengths until it fades into invisibility. However, from the vantage point of the infalling object, the transition is abrupt and final. Time, as measured by the object itself, remains unaffected, but the universe beyond the horizon recedes into darkness. The singularity at the center of the black hole, a point of infinite density and zero volume, awaits as the inevitable destination. Here, the curvature of space-time diverges to infinity, and the equations of general relativity cease to function, signaling the breakdown of the theory at the heart of modern physics. The event horizon is not a static surface, but a dynamic boundary shaped by the mass, spin and charge of the black hole. For non-rotating black holes, described by the Schwarzschild solution to Einstein's equations, the horizon is a perfect sphere with a radius proportional to the black hole's mass. Rotating black holes, governed by the Kerr metric, possess event horizons distorted by their angular momentum, forming oblate shapes with inner and outer boundaries. These intricate geometries underscore the complexity of black holes as objects, not only of immense gravity, but also of profound symmetry and mathematical elegance. The inevitability of the event horizon's grip arises from the nature of space-time itself. In the vicinity of a black hole, the curvature of space-time is so severe that all possible future trajectories of any object or photon lead inward toward the singularity. The event horizon is not a physical barrier, but a demarcation in the geometry of the universe, a point where the causal structure of space-time reorients itself. Once crossed, the direction of time and space invert. What was once a spatial dimension becomes a temporal one, and escape becomes impossible. This inversion is not a mere abstraction, but a consequence of the mathematics that govern the universe, a testament to the power of general relativity to describe phenomena beyond the reach of human intuition. Yet the event horizon's defining characteristic is not just its inescapability, but its role as a repository of information. According to the holographic principle proposed by physicists such as Gerard Hooft and Leonard Susskind, the information about the state of matter that falls into a black hole is encoded on the surface of its event horizon. This idea, though still speculative, suggests that the event horizon is more than a boundary. It is a two-dimensional representation of the three-dimensional reality within. Such a notion challenges our conventional understanding of space and information, implying that the universe may operate as a kind of cosmic code, where every action leaves an indelible mark on the fabric of reality. In essence, the event horizon is a paradox wrapped in inevitability, a place where the universe's most fundamental principles converge and collapse. It is a reminder that the cosmos is not a static tapestry, but a living, evolving entity, where the interplay of gravity, space-time, and information gives rise to phenomena that defy even the most advanced theories. As we probe deeper into the mysteries of the event horizon, we are not merely studying the behavior of black holes. We are unraveling the threads of the universe itself, seeking to understand the very nature of existence in a realm where the familiar dissolves into the extraordinary. The black hole information paradox is not merely a theoretical puzzle. It is a collision between two foundational pillars of modern physics: general relativity and quantum mechanics, each demanding its own interpretation of reality. At its core, the paradox arises from a simple yet profound question: what happens to the information carried by matter and energy that crosses the event horizon of a black hole? According to general relativity, this information is inevitably lost as it collapses into the singularity at the black hole's center, a point of infinite density where the known laws of physics break down. However, quantum mechanics, with its insistence on the conservation of information, posits that such a loss is impossible. Information in the quantum realm is not a nebulous concept but a tangible quantity, akin to energy or momentum, that must be preserved in all physical processes. The conflict between these two perspectives is stark. One theory predicts the annihilation of information, while the other demands its eternal preservation. This contradiction is not a mere academic debate. It strikes at the heart of our understanding of the universe, challenging the coherence of the frameworks we use to describe it. To appreciate the depth of this paradox, consider the implications of information loss. If information is truly destroyed within a black hole, it would violate a principle known as quantum unitarity, a cornerstone of quantum mechanics that ensures the probabilities of all possible outcomes in a system sum to 1. Unitarity implies that the evolution of a quantum system is reversible. Given the final state of a system, one should, in principle, be able to reconstruct its initial state. If information is lost in a black hole, this reversibility is shattered. The universe, as described by quantum mechanics, would become a place of irretrievable chaos, where events could occur without leaving a trace. Such a scenario is not just unsettling, it is fundamentally incompatible with the deterministic framework of quantum theory. The paradox thus exposes a critical weakness in our current understanding of black holes, suggesting that either general relativity or quantum mechanics, or both, must be incomplete. This conundrum has led physicists to explore radical possibilities to reconcile the two theories. One such proposal is the holographic principle, which posits that the information contained within a black hole is not lost but instead encoded on the surface of its event horizon. This idea, inspired by the behavior of certain string theories and quantum field theories, suggests that the three-dimensional reality of the black hole's interior can be represented as a two-dimensional hologram on the horizon. In this view, the information is not destroyed but transformed, existing in a lower dimensional form that adheres to the rules of quantum mechanics. While the holographic principle offers a tantalizing glimpse of a resolution, it remains a highly speculative concept, one that requires further mathematical rigor and experimental validation. Another approach to the paradox involves the concept of black hole complementarity, proposed by physicists such as Leonard Susskind, Lenny Thorlacius, and John Uglum. Complementarity suggests that the information about infalling matter is simultaneously preserved on the event horizon and lost in the singularity, depending on the observer's frame of reference. An external observer, peering at the black hole from afar, would see the information encoded on the horizon, while an observer falling into the black hole would experience the information collapsing into the singularity. This dual perspective, though counterintuitive, avoids the need for a single, universally valid description of the process. However, this solution is not without its own challenges. Critics argue that black hole complementarity relies on the assumption that no observer can ever verify both descriptions simultaneously, a claim that raises philosophical questions about the nature of reality and the limits of empirical knowledge. The implications of the black hole information paradox extend far beyond the confines of black holes themselves. If resolved, the paradox could provide the key to unifying general relativity and quantum mechanics, a long-sought goal in theoretical physics. The search for a theory of quantum gravity, which would seamlessly integrate the macroscopic world of space-time curvature with the microscopic realm of quantum fluctuations, hinges on reconciling these seemingly irreconcilable principles. The paradox serves as a litmus test for such theories, offering a concrete problem to solve that would validate their predictive power. Moreover, The paradox highlights the need for a deeper understanding of information in the context of the universe. In a cosmos governed by entropy and disorder, the conservation of information represents an order that transcends the apparent randomness of quantum processes. This tension between order and disorder is a recurring theme in the history of physics, from the arrow of time to the second law of thermodynamics, and the black hole information paradox adds another layer to this complex interplay. The paradox also raises profound questions about the nature of reality. If information is indeed preserved, as quantum mechanics demands, then the universe may be a kind of computational system, where every event contributes to an ever-expanding archive of data. This perspective, often referred to as the it from bit hypothesis, suggests that the fundamental building blocks of reality are not particles or fields, but bits of information. Such a view would revolutionize our understanding of the cosmos, transforming physics into an exercise in information theory rather than the study of material substances. Yet, this transformation is not without its challenges. The encoding of information on the event horizon, as proposed by the holographic principle, implies that the universe operates under constraints that are not immediately apparent. The idea that the three-dimensional reality we inhabit is a projection of a two-dimensional surface is as mind-boggling as it is elegant, a reminder that the universe may be far stranger than we dare to imagine. Ultimately, the black hole information paradox is a testament to the enduring mystery of the cosmos. It reminds us that the universe is not a static entity, but a dynamic, evolving system where the rules we take for granted may be provisional at best. The clash between general relativity and quantum mechanics is not a failure of physics, but a signpost pointing toward a deeper, more unified understanding of the universe. As we grapple with the paradox, we are not merely solving a problem, we are uncovering the boundaries of our knowledge and pushing them outward into realms where the familiar dissolves into the extraordinary. The black hole information paradox did not emerge from abstract speculation alone. It was born from a specific and unexpected discovery that sent shockwaves through the physics community. In 1974, Stephen Hawking, already renowned for his groundbreaking work in cosmology, published a paper that fundamentally altered our understanding of black holes. His findings revealed that black holes were not the eternal prisons they had been assumed to be. Instead, they could slowly lose mass and eventually evaporate over time, emitting a faint glow of thermal radiation now known as Hawking radiation. This revelation was both astonishing and deeply troubling. If black holes could decay and disappear, what happened to the information that had fallen into them? If the black hole vanished, taking its contents with it, did that information truly vanish as well? Or was there some hidden mechanism preserving it, waiting to be uncovered? Hawking's work was based on the marriage of general relativity and quantum field theory, a delicate union that had long eluded physicists. By applying quantum mechanical principles to the curved spacetime of a black hole, he demonstrated that particle-antiparticle pairs constantly form and annihilate near the event horizon due to quantum fluctuations. Normally, these virtual particles cancel each other out, but in the vicinity of a black hole, one member of the pair could fall into the singularity, while the other escapes into space. From an external observer's perspective, this appeared as if the black hole was emitting radiation, a process that gradually reduced its mass. Over time, the black hole would shrink, radiating away its energy until, in theory, it would vanish entirely. This discovery introduced a profound dilemma. If a black hole could evaporate completely, then the information that had previously been swallowed by it, whether in the form of particles, energy, or even entire stars, would seem to be lost forever. But according to the principles of quantum mechanics, information cannot simply disappear. The evolution of a quantum system must remain unitary, meaning that the probabilities of all possible outcomes must sum to 1, preserving the integrity of the system. If information was truly destroyed in the process of black hole evaporation, it would violate this fundamental tenet of quantum theory. Hawking himself initially argued that information was indeed lost, asserting that quantum mechanics would need to be modified to accommodate this reality. His conclusion was met with fierce resistance from the physics community, particularly from those who believed that the conservation of information was sacrosanct. The implications of Hawking's result were staggering. If information could be destroyed in a black hole, it would mean that the universe operated under different rules at the quantum level than at the macroscopic scale. The distinction between reversible and irreversible processes would blur, and the deterministic nature of quantum mechanics would be called into question. Moreover, the paradox highlighted a deep inconsistency between the two greatest theories of the 20th century, general relativity and quantum mechanics. For decades, physicists had struggled to reconcile these frameworks, seeking a unified theory of quantum gravity. The black hole information paradox became a focal point in this quest, a problem whose resolution might ultimately reveal the missing link between the quantum world and the large-scale structure of the cosmos. As debates raged over the fate of information in black holes, the stage was set for one of the most contentious and intellectually fertile periods in modern physics. The paradox had taken root, demanding answers that would require rethinking the very foundations of space, time, and information. And so, the search for a solution began in earnest, drawing in the sharpest minds of the era to confront the most enigmatic problem in theoretical physics. The next chapter of this story would not only test the limits of human understanding, but also shape the future of cosmology for generations to come. For centuries, black holes were considered cosmic entities beyond reach, their immense gravity trapping even light in an inescapable abyss. The prevailing belief held that nothing could ever escape a black hole's gravitational pull once it crossed the event horizon, the invisible boundary marking the point of no return. Yet in 1974, Stephen Hawking shattered this assumption with a revelation that sent ripples through the scientific community. Black holes are not eternal. Instead, they gradually lose mass and energy through a process now known as Hawking radiation. This discovery did more than challenge our understanding of black holes. It redefined the very nature of space, time, and information itself. Hawking's insight emerged from the intersection of general relativity and quantum mechanics, two pillars of modern physics that had long resisted unification. According to Einstein's theory of general relativity, black holes are regions of space-time where gravity is so intense that nothing can escape. However, quantum mechanics introduces an inherent uncertainty to the fabric of reality, allowing for fleeting fluctuations in the vacuum of space. Near the event horizon of a black hole, these quantum fluctuations give rise to pairs of virtual particles, an ephemeral dance between matter and antimatter. In most cases, these pairs annihilate each other almost instantly. But in the extreme environment near a black hole, Hawking proposed that one member of a pair might fall into the singularity while the other escapes, carrying away energy. This process, though minuscule in effect, implies that black holes emit radiation, and over vast timescales, slowly lose mass. This concept, though mathematically elegant, introduced a profound paradox. If a black hole emits radiation and eventually disappears, what happens to the information that once fell into it? In classical physics, information is never truly destroyed. Once a book is burned, its contents remain encoded in the ashes and smoke. But Hawking's calculations suggested otherwise. The radiation emitted by a black hole appeared to be purely thermal, devoid of any trace of what had been consumed. This led to what is now known as the black hole information paradox. If a black hole evaporates completely, does the information it once contained vanish from the universe? And if so, does this mean that quantum mechanics, our best description of the subatomic world, is fundamentally flawed? The implications of this paradox extend far beyond the event horizon. If information can be lost in a black hole, then the deterministic nature of quantum mechanics is called into question. The principle of unitarity, which states that the total probability of all possible outcomes of a quantum system must remain constant, would be violated. This contradiction has sparked decades of debate among physicists, many of whom believe that some unknown mechanism must preserve information, even if it defies our current understanding. As we delve deeper into the explanation of Hawking radiation, we will explore how this seemingly simple process challenges the very foundations of physics and forces us to reconsider what we know or think we know about the cosmos. At the heart of Hawking radiation lies the enigmatic behavior of virtual particles, a fundamental feature of quantum field theory. In the vacuum of space, even in the absence of observable matter, quantum fluctuations constantly generate and annihilate particle-antiparticle pairs. These fleeting entities exist only for the briefest moments before they collapse back into the void, their existence permitted by Heisenberg's uncertainty principle. However, near the event horizon of a black hole, where gravity warps spacetime to its most extreme, these quantum fluctuations take on a new significance. When a pair of virtual particles forms just outside the event horizon, the intense gravitational field can disrupt their usual fate. One particle may be pulled into the black hole, while the other escapes into the surrounding space, carrying away a small amount of energy in the form of radiation. This process, though subtle, results in a net loss of mass for the black hole, as the absorbed particle effectively subtracts from its total energy. What makes this phenomenon particularly remarkable is that it occurs despite the black hole's reputation as an inescapable trap. The particle that falls inward appears to violate the classical notion that nothing can escape a black hole's grasp. Yet the outgoing particle does precisely the opposite. From the perspective of an external observer, this radiation manifests as a faint glow emanating from the black hole's edge. While the radiation is incredibly weak for large black holes, the process accelerates as the black hole loses mass. Smaller black holes, with stronger curvature near their event horizons, experience faster evaporation rates, leading to a gradual shrinkage over eons. Eventually, if left undisturbed, a black hole will continue to radiate until it reaches a critical point, its final moments marked by a sudden burst of high-energy particles as its remaining mass collapses into a violent explosion. The randomness of Hawking radiation introduces a crucial and unsettling consequence. The emitted particles appear to carry no information about what originally fell into the black hole. Unlike a burning book, where the remnants still contain traces of the original text, the radiation produced by a black hole seems entirely disconnected from its past. This lack of correlation suggests that, over time, the information that once resided within the black hole is irretrievably lost. The universe, according to this interpretation, forgets what was consumed. But in the framework of quantum mechanics, such an idea is deeply problematic. Quantum systems evolve in a way that preserves all information, ensuring that the past is always encoded in the present. The apparent loss of information in Hawking radiation, therefore, represents a fundamental conflict between general relativity and quantum theory, one that has perplexed physicists for decades. As we contemplate the slow, flickering death of black holes, we are confronted with a profound question. If a black hole vanishes, where does the information it once contained go? The answer to this question may lie in the very fabric of quantum mechanics, where hidden correlations and entanglement might offer a means of preserving information in ways we have yet to fully understand. The exploration of this paradox is not merely an academic exercise. It forces us to confront the deepest mysteries of the universe and consider whether our current understanding of reality is incomplete. The revelation that black holes emit radiation and eventually disappear raises a profound and troubling question. If a black hole evaporates completely, what becomes of the information it once contained? In classical physics, the conservation of information is a fundamental principle. Just as energy cannot be created or destroyed, information represented by the physical state of an object must persist in some form. A book burned in a fireplace may leave behind scattered ash and heat, but its content is not truly erased. It is merely transformed and dispersed throughout the environment. Similarly, in quantum mechanics, the evolution of a system is governed by unitarity, the rule that ensures the total probability of all possible outcomes remains constant over time. This principle implies that information is never lost, only rearranged in complex, often impenetrable ways. However, Hawking radiation appears to defy this rule. The radiation emitted by a black hole is purely thermal, meaning it lacks any identifiable structure or correlation to the material that once fell into it. If a black hole were to vanish entirely, leaving behind only this featureless radiation, it would suggest that the information about its contents has been irreversibly destroyed. Such an outcome would represent a violation of the conservation of information, a cornerstone of quantum mechanics. This contradiction has led physicists to a dilemma. Either quantum mechanics must be modified to accommodate the possibility of information loss, or some unknown mechanism must be at work to preserve information in ways we do not yet understand. The first option, abandoning unitarity, is a radical proposition. If information can indeed be lost in a black hole, then the mathematical framework of quantum mechanics must be revised. This would not only challenge the predictive power of quantum theory, but also undermine the very foundation of theoretical physics, which relies on the assumption that the universe operates in a deterministic and reversible manner. The second option, modifying quantum theory to account for the behavior of black holes, is equally daunting. Any such modification would require a deep revision of our understanding of how the universe functions at the most fundamental level. Moreover, it is unclear how such changes could be experimentally verified, as black holes themselves are largely inaccessible to direct observation. Given the difficulty of altering well-established principles, many physicists have instead sought alternative explanations that preserve both quantum mechanics and the integrity of information. One such proposal is the idea that information is not truly lost, but instead encoded in the Hawking radiation in a highly scrambled and non-trivial way. According to this hypothesis, the radiation emitted by a black hole contains subtle correlations, imperceptible to current observational techniques, that carry the imprint of the information that once fell into the black hole. If true, this would imply that the information is not destroyed but rather hidden within the radiation, in a form that is exceedingly difficult to decode. However, this idea presents significant challenges. If the information is indeed preserved, it must somehow be transferred across the event horizon, the point of no return, in a way that remains consistent with the laws of physics. How such a transfer could occur is still an open question, and no definitive mechanism has yet been identified. Another approach to resolving the paradox involves rethinking the nature of the event horizon itself. Some researchers have proposed that the event horizon is not an absolute boundary, but rather a dynamic, fluctuating region where quantum effects play a dominant role. In this view, the information that enters a black hole does not simply vanish, but instead becomes entangled with the outgoing radiation in a way that prevents its complete disappearance. This idea draws upon the principles of quantum entanglement, a phenomenon in which particles become correlated in such a way that the state of one instantaneously influences the state of another, regardless of distance. If particles near the event horizon become entangled with those that escape, it is conceivable that the information carried by the infalling particles is preserved in the entangled system. However, this scenario introduces new complications, as it suggests that the event horizon is not a smooth surface, but rather a region where quantum effects dominate, potentially leading to the formation of a firewall, a hypothetical barrier of high-energy particles that would destroy anything attempting to cross the event horizon. The firewall hypothesis remains controversial, as it conflicts with the equivalence principle of general relativity, which states that an observer falling into a black hole should not experience any dramatic effects at the event horizon. Beyond these theoretical considerations, the black hole information paradox has profound philosophical implications. If information is truly lost in a black hole, it would suggest that the universe is not as deterministic as we have long assumed. Instead of a closed system where every event has a definite cause and effect, the universe might operate according to a different set of rules, where information can be irreversibly erased. This possibility challenges the very nature of knowledge itself. If the past can be forgotten, then the future may not be entirely predictable. On the other hand, if information is preserved in some hidden form, it implies that the universe maintains a kind of cosmic memory, even if we lack the means to access it. This notion resonates with the broader theme of entropy and the arrow of time, as it suggests that the universe progression from order to disorder may be more nuanced than previously thought. Ultimately, the black hole information paradox remains one of the most pressing unresolved questions in theoretical physics. It forces us to confront the limitations of our current understanding, and to consider whether the fundamental laws of nature may require a radical re-examination. As we explore these ideas further, we begin to see that the answer may not lie solely in modifying existing theories, but in uncovering a deeper, unified framework that reconciles general relativity and quantum mechanics. The search for such a framework is the subject of ongoing research, and it may ultimately reveal a new picture of reality, one in which information is not lost, but merely transformed in ways we have yet to comprehend. As we grapple with the paradox of information loss in black holes, the solution may lie in one of the most enigmatic and counterintuitive aspects of quantum mechanics: entanglement. First predicted in the early days of quantum theory, entanglement describes a deep and mysterious connection between particles that persists regardless of the distance separating them. When two particles become entangled, their properties are linked in such a way that the measurement of one instantly determines the state of the other, no matter how far apart they may be. This phenomenon, famously described by Einstein as spooky action at a distance, defies classical intuition and challenges our conventional understanding of locality and causality. Yet, despite its strange nature, entanglement is not merely a theoretical curiosity. It plays a fundamental role in the fabric of reality, shaping the behavior of particles at the smallest scales and influencing the very structure of the cosmos. In the context of black holes, entanglement offers a tantalizing possibility. If information is not lost, perhaps it is encoded in the entangled relationships between particles, allowing it to persist even after the black hole has evaporated. According to this idea, the outgoing Hawking radiation is not a random emission of particles, but rather a carefully orchestrated exchange of quantum information. When a pair of entangled particles forms near the event horizon, one may fall into the black hole, while the other escapes, carrying away a piece of the quantum state of its entangled partner. If this entanglement is preserved, then the information that entered the black hole is not destroyed but instead distributed across the outgoing radiation in a highly complex and non-local manner. This hypothesis, if correct, would resolve the paradox by ensuring that the information is not lost, but rather encoded in the correlations between particles, even if it is not immediately accessible to an external observer. However, this explanation introduces a new layer of complexity. For entanglement to serve as a mechanism for preserving information, it must function across the event horizon in a way that is consistent with both quantum mechanics and general relativity. This requirement leads to a deeper question: how can entanglement bridge the divide between the interior and exterior of a black hole? One possibility is that entangled particles maintain their connection, even as one crosses the event horizon, forming a network of correlations that spans both sides of the black hole. If this is the case, then the information that enters the black hole is not confined to its interior, but is instead shared between the infalling particle and its outgoing counterpart. This idea aligns with recent theoretical developments, such as the ER-RETPR conjecture, which proposes a deep relationship between entanglement and the geometry of space-time itself. According to this hypothesis, entangled particles are connected by microscopic wormholes, suggesting that the fabric of the universe may be woven together by these hidden quantum threads. The implications of this perspective are profound. If entanglement serves as a bridge between the interior and exterior of a black hole, then the information that enters a black hole is not truly lost. It is simply encoded in the intricate web of quantum correlations that extend beyond the event horizon. This view shifts the focus from the question of where information goes to how it is preserved and transmitted, rather than seeking a direct trace of the infalling material in the Hawking radiation. We must look for the subtle patterns of entanglement that bind the outgoing particles to their partners within the black hole. This line of reasoning suggests that the information is not missing, but is instead distributed in a way that is currently beyond our ability to decode. If this is the case, then the resolution of the black hole information paradox may not require a fundamental change to the laws of physics, but rather a deeper understanding of how information is stored and communicated in the quantum realm. As we continue to explore these ideas, we find ourselves standing at the threshold of a new frontier in theoretical physics. The study of entanglement in the context of black holes may not only shed light on the fate of information, but also provide insights into the nature of space-time itself. The interplay between quantum mechanics and general relativity has long been one of the greatest unsolved problems in science, and the resolution of the information paradox may ultimately lead to a unified theory that encompasses both, whether through entanglement, hidden correlations, or some yet undiscovered mechanism. The answer to this puzzle may lie in the intricate dance of particles that governs the universe at its most fundamental level. With this in mind, we turn our attention to the broader implications of entanglement, not just in the context of black holes, but in the very architecture of the cosmos itself. In the vast expanse of the cosmos, where stars are born in fiery nurseries and galaxies spiral in slow celestial waltzes, there exists a fundamental mystery that defies classical intuition. At the heart of this enigma lies quantum entanglement, a phenomenon so counterintuitive that even Albert Einstein, who laid the foundation of modern physics, famously dismissed it as spooky action at a distance. Yet decades of experiments have confirmed its reality, revealing a deep connection between particles that transcends the limitations of space and time. This peculiar property of quantum mechanics suggests that two particles, once entangled, remain inextricably linked, no matter how far apart they drift across the universe. If one particle is measured and its state is determined, the other instantaneously collapses into a corresponding state, even if they are light years apart. This instantaneous correlation challenges our classical understanding of locality, where cause and effect are bound by the speed of light. Quantum entanglement is not merely an abstract curiosity. It is a cornerstone of modern physics, with profound implications for our understanding of the universe. Its effects are not limited to the subatomic realm, but ripple outward, influencing the behavior of particles, fields, and perhaps even the fabric of space-time itself. In the context of black holes, where gravity warps the very essence of reality, entanglement may play a crucial role in resolving one of the most perplexing questions in theoretical physics. What happens to information that falls into a black hole? According to general relativity, nothing, not even information, can escape the gravitational pull of a black hole once it crosses the event horizon. However, quantum mechanics suggests that information cannot simply vanish. It must be preserved in some form. This contradiction has led to the development of the black hole information paradox, a conundrum that continues to challenge physicists and reshape our understanding of the cosmos. At the core of this paradox lies the concept of Hawking radiation, a phenomenon proposed by Stephen Hawking in the 1970s. According to his calculations, black holes are not entirely black. Instead, they emit faint radiation due to quantum fluctuations near the event horizon. These fluctuations create pairs of particles, one with positive energy and one with negative energy, where the positive particle escapes as Hawking radiation, while the negative one falls into the black hole. This process gradually reduces the mass of the black hole, causing it to evaporate over time. However, this raises a critical issue. If a black hole eventually disappears, where does the information it once contained go? If the information is truly lost, it would violate the principles of quantum mechanics, which demand that information is never destroyed. Some physicists propose that entanglement may provide a solution to this paradox, suggesting that the information is not lost but encoded in the correlations between entangled particles. This tantalizing idea opens the door to a deeper understanding of the relationship between quantum mechanics and gravity, hinting at a hidden order within the chaos of the cosmos. To grasp the full scope of quantum entanglement, one must first understand the fundamental nature of entangled particles, how they defy classical expectations. At the quantum level, particles such as electrons, photons, or even atoms can become entangled through interactions that bind their quantum states together. Once entangled, these particles exist in a shared quantum state, meaning their properties are interdependent, regardless of the distance separating them. This phenomenon was famously illustrated in the Einstein-Podolsky-Rosen (EPR) thought experiment, which attempted to challenge the completeness of quantum mechanics by highlighting what seemed to be an absurd consequence of entanglement, that measuring one particle would instantaneously determine the state of another, no matter how far apart they were. However, subsequent experiments, particularly those involving Bell's theorem and the violation of Bell inequalities, have confirmed that quantum entanglement is not only real but a fundamental feature of nature. These experiments demonstrated that the correlations between entangled particles exceed what classical physics would predict, reinforcing the notion that quantum mechanics operates under fundamentally different rules than classical theories. One of the most striking demonstrations of entanglement occurs in laboratory settings, where scientists create pairs of entangled photons. When these photons are emitted from a common source, they become correlated in such a way that their polarization states are linked. If one photon is measured and found to have a vertical polarization, its entangled partner will instantly exhibit a horizontal polarization, even if they are separated by vast distances. This instantaneous correlation appears to transcend the constraints of space and time, as if the particles are in constant communication, despite having no direct means of interaction. However, it is essential to clarify that this correlation does not allow for faster-than-light communication in a way that could transmit meaningful information. Instead, the measurement outcomes are random, and any attempt to use entanglement to send messages results in a sequence of random numbers, not a coherent signal. This distinction is crucial in understanding how entanglement functions within the framework of quantum mechanics, as it ensures that the theory remains compatible with the principles of relativity, which prohibit true superluminal signaling. Yet the implications of entanglement extend beyond mere laboratory curiosities. In the context of black holes, entanglement may serve as a bridge between quantum mechanics and general relativity, offering a potential resolution to the black hole information paradox. When Hawking radiation is emitted from the vicinity of a black hole, it is theorized that the outgoing particle is entangled with its infalling counterpart. As the black hole evaporates over time, the outgoing radiation carries away energy, while the infalling particle contributes to the black hole's gradual disappearance. However, if the outgoing radiation is entangled with the infalling particle, then the information associated with that entangled state must somehow persist, even as the black hole vanishes. This raises a critical question. If the black hole completely evaporates, where does the entangled information go? One possibility is that the information is not lost but rather encoded in the correlations between successive emissions of Hawking radiation. In this scenario, the information is not stored in individual particles, but distributed across the entire ensemble of emitted radiation, forming a complex web of quantum correlations that could, in principle, be reconstructed if one had access to the complete history of the black hole's evaporation. This idea introduces a radical shift in how we perceive information in the universe. Traditionally, information has been understood as something that resides within objects or systems, much like data stored in a computer. However, the entanglement-based perspective suggests that information is instead woven into the fabric of quantum correlations, existing not as a fixed quantity, but as a dynamic network of relationships. From this viewpoint, the loss of information into a black hole is not an absolute destruction, but a transformation of that information into a form that is not immediately accessible. Just as a message written in invisible ink becomes legible only under specific conditions, the information trapped within a black hole may be concealed in the intricate patterns of entangled particles, waiting to be deciphered by a sufficiently advanced observer. This notion challenges our conventional understanding of entropy and information conservation, hinting at a deeper, more interconnected structure to the cosmos than previously imagined. As physicists continue to probe the mysteries of entanglement, its role in black holes remains a subject of intense study. Theoretical models suggest that if entanglement extends across the event horizon, it could provide a mechanism for information to escape from the black hole's grip. This would imply that the information is not lost, but instead encoded in the correlations between the outgoing Hawking radiation and the remnants of the black hole itself. However, the feasibility of retrieving this information remains a formidable challenge. Extracting the hidden correlations would require an observer with access to the entire history of the black hole's evaporation, capable of performing computations of unimaginable complexity. The sheer scale of this task underscores the immense difficulty of reconstructing lost information. Yet it also highlights the profound implications of entanglement in shaping the fate of information in the universe. If entanglement indeed extends across the event horizon of a black hole, the implications for information preservation are staggering. At first glance, it may seem as though the information swallowed by a black hole is irretrievably lost, buried beneath layers of space-time curvature and gravitational distortion. But from the vantage point of quantum mechanics, information is not a static entity confined to physical objects. It is a dynamic pattern, a web of correlations woven into the very fabric of reality. In this view, the information that falls into a black hole is not destroyed but transformed, encoded in the delicate dance of entangled particles. The outgoing Hawking radiation, once thought to be purely thermal noise, may instead carry imprints of the information that once resided within the black hole's interior. This revelation reshapes our understanding of black holes, transforming them from ultimate sinks of information into complex reservoirs where data is subtly encoded in the correlations between particles. However, the challenge of extracting this information is as daunting as it is fascinating. Consider the analogy of a library reduced to ashes. The books themselves are gone, their physical pages turn to dust and smoke. Yet, in principle, the information they contained could still exist in the molecular arrangement of the smoke, the heat radiated into the air, and the patterns left behind in the embers. Reconstructing the contents of those books would require an observer with the ability to analyze every particle of smoke, trace the trajectory of each molecule, and decode the hidden relationships that once defined the text. Similarly, the information contained within a black hole may be dispersed in the correlations of Hawking radiation, but retrieving it would demand a level of precision and computational power that borders on the impossible. What makes this task so difficult is the sheer complexity of the entangled state. Unlike a simple message written in a book, the information encoded in entangled particles is not localized in any one place. Instead, it is spread across an astronomical number of quantum correlations, each one contributing to the overall pattern in ways that are not immediately apparent. To extract the information, an observer would need to perform an operation known as quantum tomography, an exhaustive process of measuring the properties of entangled particles to reconstruct the original quantum state. However, this process requires an enormous number of measurements, each one yielding only a fragment of the total information. In the case of a black hole, where the entangled state is constantly evolving as the black hole evaporates, the problem becomes even more formidable. The observer would need to track not just the current state of the Hawking radiation, but also its entire history, ensuring that no correlations are missed or misinterpreted. Moreover, the act of measurement itself introduces additional complications. In quantum mechanics, the act of observing a system inevitably alters its state. When dealing with entangled particles, this means that any attempt to extract information from one part of the system will influence the state of the other parts. This phenomenon, known as quantum backaction, makes it extremely difficult to obtain a complete picture of the entangled state without introducing errors. Furthermore, the information encoded in the entangled particles is not directly accessible. It must be inferred from the statistical correlations between multiple measurements. This means that the observer must collect an immense amount of data and then perform a series of complex mathematical operations to extract the hidden information. Even if this were possible, the resulting information would be highly fragmented, requiring further processing to reconstruct the original message. Given these challenges, it is clear that extracting information from a black hole is not a simple matter of reading a message from a distant source. It is a process that demands not only an unprecedented level of observational precision, but also a computational capacity that far exceeds anything currently available. The universe itself may serve as the ultimate quantum computer, with the laws of physics acting as the algorithm that encodes and processes information. In this sense, the information contained within a black hole may not be lost, but rather hidden in the vast complexity of quantum correlations, waiting to be deciphered by an observer with the right tools and knowledge. Yet, even if the information is preserved in this way, the question remains, can it ever be fully retrieved? The answer depends on the nature of the correlations and the limitations imposed by the laws of physics. In some cases, the information may be recoverable in principle, but in practice, the required resources may be so immense that it becomes effectively inaccessible. Other scenarios suggest that certain types of information may be irreversibly scrambled, making reconstruction impossible even in theory. This ambiguity underscores the profound uncertainty surrounding the fate of information in the universe. Is information a fundamental property of reality, one that must always be conserved, or is it a construct that can be lost in the chaotic churn of the cosmos? These questions take on even greater significance when considering the broader implications of entanglement for the structure of the universe. If entanglement allows information to persist beyond the event horizon of a black hole, It suggests that the universe is not a collection of isolated entities, but a deeply interconnected whole. Every particle, every wave of radiation, and every ripple in space-time may be part of a vast quantum network, where information is not confined to individual objects, but distributed across the entire cosmos. This perspective challenges our traditional notions of separability and independence, suggesting that the boundaries we draw between things, between the observer and the observed, between the inside and the outside of a black hole, are ultimately artificial constructs. From this viewpoint, the black hole is not an endpoint, but a node in a grander network of entanglement. The information it consumes is not destroyed but redistributed, flowing into the quantum correlations that define the fabric of reality. The outgoing Hawking radiation may carry echoes of the past, whispers of the information that once existed within the black hole's interior, and if an observer was somehow able to trace the full history of these correlations, they might glimpse the secrets of the universe itself, unraveling the hidden connections that bind all things together. Yet, for all its promise, this vision remains shrouded in uncertainty. The mechanisms by which information is encoded in entanglement are still poorly understood, and the feasibility of retrieving it remains a subject of intense debate. Some physicists argue that the information may be preserved in a way that is fundamentally inaccessible, while others propose alternative models in which information is either lost or stored in a form that defies conventional description. These differing perspectives reflect the deep philosophical questions that underlie the study of black holes and quantum mechanics. Are we witnessing the limits of human knowledge, or are we simply missing the right tools to unlock the universe's deepest secrets? As we stand at the intersection of quantum mechanics and general relativity, the mystery of black holes continues to push the boundaries of our understanding. The entanglement of particles, once dismissed as a mere curiosity, now stands at the forefront of our quest to reconcile the quantum world with the macroscopic universe. Whether or not the information hidden within a black hole can ever be fully retrieved, the pursuit of this knowledge reveals something profound about the nature of reality itself. In the endless dance of entangled particles, we glimpse the possibility that the universe is not a collection of separate pieces, but a unified whole, where every action ripples across the fabric of existence, connecting us to the farthest reaches of space and time. Yet, even if entanglement provides a pathway for information to escape the clutches of a black hole, another fundamental obstacle looms on the horizon. At the heart of quantum mechanics lies an unyielding rule: information cannot be copied. This principle, known as the no-cloning theorem, asserts that it is impossible to duplicate an arbitrary unknown quantum state without altering the original. While classical information, such as the binary code of a digital message, can be freely replicated, quantum information is far more elusive. Any attempt to copy it disrupts the delicate balance of superposition and entanglement, rendering the process fundamentally flawed. This restriction places an insurmountable barrier in the path of observers attempting to retrieve information from a black hole, for if the information is encoded in entangled particles, it cannot be duplicated without destroying the very correlations that preserve it. This realization gives rise to a new paradox, one that intertwines the fate of information with the laws of quantum mechanics in a way that defies intuition. If the information within a black hole is preserved through entanglement, then the outgoing Hawking radiation must carry a unique quantum signature that reflects the state of the infalling matter. However, if an observer attempts to measure this radiation in order to extract the information, the act of observation itself alters the state of the entangled system. This creates a dilemma. The information is preserved in the correlations between particles, yet the moment it is accessed, it is irrevocably changed. In essence, the observer is faced with a choice: either leave the information untouched and forever inaccessible, or measure it and risk distorting the very information they seek to recover. This paradox deepens when one considers the nature of quantum measurements and the principle of quantum coherence. In a typical quantum experiment, the observer's measurement collapses the quantum state into a definite outcome, destroying the superposition that once defined the system. If the information within a black hole is encoded in such a fragile state, then any attempt to observe it would collapse the entanglement, rendering the information unreadable. This suggests that the information may exist in a form that is fundamentally incompatible with direct observation, hidden in a quantum state that cannot be measured without disrupting its integrity. In this light, the black hole information paradox is not merely a question of whether information is lost or preserved. It is a fundamental challenge to the very nature of observation itself. The implications of this paradox extend beyond the confines of black holes, touching upon the foundational principles of quantum mechanics and the limits of knowledge. If certain types of information are inaccessible due to the constraints of quantum mechanics, then our understanding of the universe must necessarily remain incomplete. The very act of observation imposes restrictions on what can be known, forcing us to accept that some aspects of reality may forever elude our grasp. This realization echoes the uncertainty principle, which dictates that certain properties of a quantum system cannot be simultaneously known with perfect precision. In this context, the inability to copy quantum information is not a limitation of technology, but a fundamental law of nature, one that defines the boundaries of what can be known and what must remain hidden. This leads to a profound question. If information cannot be copied, can it truly be said to exist in a way that is independent of observation? The Copenhagen interpretation of quantum mechanics suggests that the act of measurement plays a central role in defining reality, implying that information is not an objective property, but rather something that emerges through the process of observation. On the other hand, alternative interpretations, such as the many worlds hypothesis, propose that all possible outcomes of a quantum measurement coexist in parallel universes, allowing information to be preserved in an infinite branching of realities. These competing views highlight the deep philosophical divide in our understanding of quantum mechanics, a division that becomes even more pronounced when applied to the extreme conditions of a black hole. As physicists grapple with these questions, new models and hypotheses continue to emerge, each offering a different perspective on the nature of information and its fate in the cosmos. Some researchers propose that the information is not lost, but instead stored in a form that is inaccessible to external observers, while others suggest that the very fabric of space-time is encoded in the correlations between entangled particles, giving rise to a holographic description of the universe. These ideas challenge our conventional notions of space, time, and causality, pushing the boundaries of theoretical physics into uncharted territory. Ultimately, the paradox of information and the limits of observation force us to confront the deepest mysteries of the universe. Are we merely passive observers, constrained by the laws of physics and the limitations of our instruments, or do we have the potential to uncover the hidden structure of reality? The answers may lie not in the black holes themselves, but in the fundamental principles that govern the quantum world, where entanglement, uncertainty, and the irreversibility of observation shape the very fabric of existence. As we continue to explore these enigmas, we find ourselves standing at the precipice of discovery, gazing into the vast unknown, where the secrets of the cosmos await our understanding. In the vast, silent expanse of the cosmos, where stars are born in the cradles of nebulae and galaxies spiral in eternal dances, lies a realm governed by rules so alien to our everyday experience that they seem plucked from the pages of a poet's dream. Here, in the quantum domain, the laws of physics twist and shimmer like light refracted through a prism. Among these laws, one stands as a quiet sentinel, enforcing a boundary as immutable as gravity itself, the no-cloning theorem. This principle, a cornerstone of quantum mechanics, declares that a quantum state cannot be perfectly replicated. It is not merely a restriction, but a fundamental truth etched into the fabric of reality. To violate it would be to defy the very essence of what it means to exist in a universe where particles are waves, and information is both fragile and infinite. Yet the theorem's simplicity belies its profound implications. Consider the black hole, a celestial object so dense and mysterious that even light cannot escape its gravitational pull. These cosmic voids, born from the collapse of massive stars, have long been enigmatic symbols of entropy and finality. But what happens when a quantum state, say the spin of a photon or the polarization of an electron, plunges into a black hole's abyss? According to Einstein's theory of general relativity, the information carried by that state is swallowed whole, lost forever behind the event horizon. Yet quantum mechanics insists that information must endure, never truly erased. This collision of principles, the clash between gravity's finality and quantum immortality, gives rise to a paradox so confounding that it challenges the foundations of modern physics. If the black hole's event horizon were to emit copies of the ingested quantum state, as suggested by Hawking radiation, the no-cloning theorem would be violated. Information would exist in two places at once, a violation as unthinkable as a shadow existing without a source. Thus, the black hole becomes not just a destroyer of matter, but a crucible for the deepest mysteries of existence, where the sanctity of information is tested against the extremes of space-time. To navigate this conundrum, we must first understand the nature of quantum information and why it cannot be copied, unlike classical data, which can be transcribed or duplicated with ease. A book can be printed again and again, a digital file transferred across networks. Quantum information is bound by the peculiarities of superposition and entanglement. A qubit, the fundamental unit of quantum information, exists in a probabilistic cloud of states until measured, its identity fragmented across possibilities. Copying such a state is not a matter of replication, but of transformation, and the mathematics of quantum mechanics forbids this transformation without altering the original. The no-cloning theorem is thus not a mere technicality, but a reflection of the universe's refusal to allow perfect duality. Yet, in the presence of a black hole, this rule is brought to a breaking point. Hawking radiation, the faint glow emitted by black holes as they slowly evaporate, hints at a process where information might escape, but at what cost? Is the universe willing to sacrifice its own laws to preserve the coherence of its quantum tapestry? As we peer into the heart of this paradox, we find ourselves standing at the edge of a precipice, where the answers may force us to rewrite the very story of reality. At the core of the no-cloning theorem lies a deceptively simple statement. A quantum system in an arbitrary unknown state cannot be duplicated. This is not a limitation imposed by technological constraints or observational error, but a mathematical certainty derived from the axioms of quantum mechanics. The proof is elegant in its abstraction. Suppose we attempt to create a copy of a quantum state using a universal copying machine. Such a machine would need to take an input state and a blank state, 0, and produce B in chain. However, the linearity of quantum operations prohibits this, unless B is already known, a condition that negates the purpose of copying. In essence, the theorem reveals that the act of copying disrupts the delicate balance of superposition, forcing the system into a state that violates the principles of quantum coherence. This prohibition becomes starkly relevant when considering the interplay between black holes and Hawking radiation. In 1974, Stephen Hawking revolutionized our understanding of black holes by demonstrating that they are not entirely black. Due to quantum fluctuations near the event horizon, virtual particle-antiparticle pairs constantly pop in and out of existence. Occasionally, one of these particles falls into the black hole, while its partner escapes as radiation. Over eons, this process causes the black hole to lose mass and eventually evaporate. Crucially, Hawking's calculations suggested that the escaping radiation carries no information about the black hole's internal state. It is purely thermal, a random soup of particles. If this is true, then the information that once fell into the black hole, its history, its quantum states, is irretrievably lost. This conclusion, however, directly contradicts the principle of unitarity in quantum mechanics, which demands that information must be conserved. Herein lies the paradox. If the black hole evaporates completely, the information it once contained vanishes, violating quantum mechanics. But if the information instead escapes via Hawking radiation, it must do so in a way that duplicates the original state. The problem is that such duplication would break the no-cloning theorem, as the same quantum state would exist both inside the black hole and outside in the radiation. This contradiction is not a mere academic curiosity. It strikes at the heart of whether the universe operates under consistent deterministic laws. Physicists have grappled with this dilemma for decades, proposing solutions that range from the plausible to the fantastical. Some argue that the information is not truly lost but encoded in subtle correlations within the Hawking radiation, hidden in the statistical noise. Others suggest that the black hole's evaporation halts before complete disappearance, leaving behind a remnant that preserves the information. Still, others entertain the possibility that quantum mechanics itself must be revised, allowing for exceptions to the no-cloning rule in extreme conditions. Yet none of these ideas have gained universal acceptance, and the paradox persists as an open wound in the theoretical framework of physics. The stakes are immense. Resolving this paradox requires reconciling two pillars of modern science: general relativity, which governs the behavior of massive objects and the curvature of space-time, and quantum mechanics, which describes the probabilistic nature of subatomic particles. Black holes are the ultimate proving ground for this synthesis, as they embody the extremes of both theories. At the event horizon, where the gravitational pull becomes infinite and the laws of physics as we know them cease to apply, the fate of information becomes a test of whether our current models are incomplete or fundamentally flawed. The no-cloning theorem, in this context, is not merely a rule but a litmus test for the coherence of reality itself. If the theorem is violated, it implies that either quantum mechanics or general relativity must yield to a deeper, unified theory, one that has yet to be discovered. Until then, the black hole remains a cosmic riddle, its event horizon, a veil behind which the universe guards its most intimate secrets. The black hole information paradox has forced physicists to confront the possibility that our understanding of reality is far more fragile than we dare to believe. At stake is not only the fate of information, but the very architecture of existence. One proposed resolution, known as quantum teleportation, offers a tantalizing glimpse into how the no-cloning theorem might be upheld even in the face of apparent duplication. In quantum teleportation, a particle's state is not copied, but transferred to another particle through entanglement, a phenomenon where two particles become correlated regardless of distance. By leveraging entanglement, the original state is destroyed in the process of transmission, ensuring that no perfect duplicate is created. Could this principle extend to black holes? Perhaps the information falling into a black hole is not lost but teleported to the outgoing Hawking radiation, preserving the no-cloning theorem by annihilating the original state within the black hole. Yet this idea hinges on the assumption that entanglement can span the chasm between the singularity and the event horizon, a notion that stretches the limits of current quantum field theory. Another radical hypothesis suggests that the universe actively prevents observers from witnessing violations of the no-cloning theorem. This idea, often framed in terms of the cosmic censorship conjecture, posits that any attempt to observe a duplication of quantum states results in the destruction of the observer. Imagine a daring astronaut equipped with instruments capable of measuring the Hawking radiation and the contents of the black hole. If the information indeed exists in two places at once, the act of measurement would trigger a catastrophic cascade of quantum effects, collapsing the system into a state where the duplication is erased. In this view, the universe is not merely governed by rules, but by a kind of self-preservation instinct, ensuring that its foundational principles remain unbroken. While poetic, this scenario raises unsettling questions. Who or what defines the boundaries of permissible observation? Does the universe possess a will, or is this an emergent property of its underlying mathematics? Some theorists have turned to the holographic principle for insight, a radical concept suggesting that all the information contained within a volume of space can be represented as a lower-dimensional hologram on its boundary. Applied to black holes, this principle implies that the information falling into a black hole is not lost but encoded on the event horizon itself. From this perspective, the paradox dissolves because there is no true duplication, only a dual representation of the same information. The interior and exterior of the black hole are not separate realms, but complementary aspects of a single reality, much like the front and back of a mirror. This idea, though mathematically elegant, challenges our intuitive sense of locality, requiring us to accept that the three-dimensional world we inhabit is an illusion, a projection from a two-dimensional substrate. If correct, the holographic principle would redefine not only black holes, but the entire cosmos, suggesting that the universe is a vast, interconnected code where every bit of information is both singular and infinite. Yet, for all their ingenuity, these proposals remain speculative. They offer glimpses of possible resolutions, but lack the empirical validation needed to transcend the realm of theory. This uncertainty is both humbling and exhilarating. a reminder that the universe is not a puzzle to be solved, but a living mystery that defies easy answers. The no-cloning theorem, once a quiet rule of quantum mechanics, has become a lens through which we examine the very nature of existence. In its defiance of duplication, it whispers of a cosmos where identity is sacred, where every quantum state is a unique thread in the tapestry of reality. And yet, the black hole, with its voracious hunger and enigmatic glow, reminds us that the universe is not static. It is a dynamic, evolving entity, and the laws that govern it may themselves be subject to revision. As we stand on the threshold of understanding, we are left with a choice: to cling to the familiar or to embrace the unknown, knowing that the answers we seek may lie beyond the limits of our imagination. If the universe resists the duplication of information, what force could compel it to bend its own rules? One of the most audacious proposals to emerge from the black hole paradox is the Firewall hypothesis, a concept so radical that it has sparked fierce debate among physicists. The idea suggests that the event horizon of a black hole is not the smooth, featureless boundary predicted by general relativity, but a seething wall of energy, a firewall that incinerates anything that dares to cross it. This violent curtain, proponents argue, would destroy the quantum state of infalling matter before it could become entangled with the outgoing Hawking radiation, thereby preserving the no-cloning theorem. But the firewall hypothesis is a double-edged sword. While it may resolve the paradox, it also violates the equivalence principle, a cornerstone of Einstein's theory, which holds that an observer in free fall should not experience anything unusual at the event horizon. The implication is clear: either quantum mechanics triumphs over general relativity, or the two must be reconciled in ways we have yet to comprehend. As we venture further into this labyrinth of ideas, the next segment will delve into the firewall hypothesis and its ramifications. What does it mean for the fate of an observer who plunges into a black hole? Does the universe burn away the evidence of its own contradictions, or is there a deeper harmony waiting to be uncovered? The answers may lie not in the destruction of information, but in the transformation of our understanding itself. At the edge of a black hole lies one of the most enigmatic boundaries in the cosmos, the event horizon. For decades, physicists envisioned this threshold as a silent, invisible curtain, a point of no return where the laws of classical physics dissolve into the abyss. Yet recent theoretical explorations have challenged this notion, suggesting that the event horizon might not be a passive gateway, but a seething, energetic inferno. The firewall hypothesis, a radical proposition born from the collision of quantum mechanics and general relativity, posits that any object or observer daring to cross this boundary would meet an instantaneous and catastrophic fate. Instead of gliding into the singularity as Einstein's equations once implied, an intruder would be incinerated by an invisible wall of high-energy particles. This idea, though unsettling, arises from a desperate attempt to reconcile two foundational pillars of modern physics: the conservation of information in quantum systems and the smooth, continuous fabric of space-time described by general relativity. The stakes are profound. If firewalls exist, they would rewrite our understanding of black holes, the nature of reality itself, and the very possibility of traversing the cosmos. To grasp the significance of this hypothesis, we must first journey into the heart of the paradox that birthed it, a conflict so deep it has left even the sharpest minds of our time in disarray. The event horizon, as traditionally conceived, is a region where gravity becomes so intense that not even light can escape. According to Einstein's theory of general relativity, space-time curves seamlessly into the singularity. At a black hole's center, an astronaut falling into a black hole, according to this framework, should experience no immediate trauma. Their descent would feel no different from floating freely in empty space. This principle, known as the equivalence principle, underpins much of our understanding of gravity. Yet when quantum mechanics enters the equation, the picture fractures. Stephen Hawking's groundbreaking work in the 1970s revealed that black holes emit radiation, a phenomenon now known as Hawking radiation. This discovery, while elegant, introduced a paradox. If information about the matter that falls into a black hole is irretrievably lost, it violates the fundamental tenets of quantum mechanics. which demand that information is never truly destroyed. The firewall hypothesis emerged as a potential resolution to this conundrum, proposing that the very act of preserving information forces the universe to unleash a violent upheaval at the event horizon. Thus, the quiet, uneventful descent into a black hole becomes a fiery cataclysm. This hypothesis, though controversial, compels us to reconsider the nature of reality. If true, firewalls would represent a fundamental breakdown of general relativity at the event horizon, a rupture in the cosmic tapestry that Einstein once described as smooth and unbroken. Such a scenario would not only upend our understanding of black holes, but also force a reckoning between the two great theories that govern the universe. Quantum mechanics, with its probabilistic nature and insistence on information preservation, clashes with general relativity's deterministic, geometric vision of spacetime. The firewall hypothesis is not merely a fringe idea. It is a symptom of a deeper crisis in physics, a sign that our current frameworks may be incomplete or incompatible. As we delve further into this hypothesis, we confront a question that has haunted physicists for generations. Can the universe coexist peacefully under the rule of both quantum mechanics and general relativity, or must one yield to the other? The answer may lie in the very fabric of the cosmos, hidden within the shimmering veil of the event horizon. To understand the firewall hypothesis, we must begin with the quantum process that gives rise to Hawking radiation. In the vacuum surrounding a black hole, virtual particle-antiparticle pairs constantly flicker in and out of existence due to the Heisenberg uncertainty principle. These ephemeral fluctuations are typically short-lived, as the particles annihilate each other almost instantaneously. However, near the event horizon, the immense gravitational pull of the black hole can disrupt this balance. One member of a particle pair may fall into the black hole, while the other escapes into space. From an external perspective, this escaping particle appears as radiation emitted by the black hole, a phenomenon Hawking famously dubbed Hawking radiation. Over time, this process causes the black hole to lose mass and eventually evaporate. Yet here lies the rub. The entanglement between the infalling and outgoing particles creates a paradox. In quantum mechanics, entangled particles share a deep connection. The state of one instantly influences the state of the other, regardless of distance. When one particle escapes as Hawking radiation, the other remains trapped within the black hole. If the black hole evaporates completely, this entangled relationship is severed, a process known as entanglement breaking. But entanglement breaking is not a trivial event. It releases energy, often in the form of high-energy particles. This energy, concentrated at the event horizon, manifests as a firewall. The mathematics of quantum field theory suggests that the energy required to break entanglement is enormous, sufficient to incinerate anything attempting to cross the horizon. This conclusion, however, directly contradicts the equivalence principle, a cornerstone of general relativity. According to Einstein, an observer in free fall should not perceive any extraordinary effects at the event horizon. Their experience should mirror that of floating in empty space. The equivalence principle is not merely a theoretical abstraction. It is a principle that has been tested and confirmed in countless experiments, from the bending of starlight during solar eclipses to the precise operation of GPS satellites. The firewall hypothesis, therefore, poses a profound challenge. If the equivalence principle fails at the event horizon, then general relativity as we know it must be incorrect. Yet abandoning the equivalence principle is equally untenable, as it forms the bedrock of our understanding of gravity. The paradox deepens when we consider the perspective of an external observer. From their vantage point, the infalling object appears to slow down and freeze at the event horizon, a consequence of time dilation in strong gravitational fields. Meanwhile, the firewall, if it exists, would appear as a sudden burst of energy at the horizon. How can these two seemingly contradictory phenomena coexist? The answer lies in the tension between quantum mechanics and general relativity. Quantum mechanics demands that information about the infalling object is preserved in the outgoing Hawking radiation, while general relativity insists that the object must pass unscathed into the black hole. The firewall hypothesis resolves this by asserting that the preservation of information forces a violent disruption at the horizon, an act of cosmic self-preservation. This scenario raises a troubling question. Is the universe willing to sacrifice the smoothness of space-time to uphold the principles of quantum mechanics? The firewall hypothesis suggests that it is. By creating a barrier of energy at the event horizon, the universe ensures that information is neither lost nor duplicated, adhering strictly to the rules of quantum mechanics. Yet this comes at a cost. The equivalence principle, a fundamental symmetry of nature, is violated. An observer falling into a black hole would not experience the gentle descent predicted by general relativity, but would instead be vaporized by the firewall. This outcome is so drastic that many physicists have resisted it, seeking alternative explanations for the information paradox. Still, the firewall hypothesis remains a compelling if unsettling possibility, one that forces us to confront the limits of our current understanding. The implications of the firewall hypothesis extend far beyond the event horizon, challenging the very foundations of modern physics. If firewalls exist, they represent a catastrophic failure of general relativity at the scale of black holes, a realm where gravity reigns supreme. General relativity has long been celebrated for its ability to describe the curvature of space-time, from the orbits of planets to the expansion of the universe. Yet the firewall hypothesis exposes a critical flaw in this framework. It cannot account for the quantum nature of the vacuum. The smooth, continuous fabric of space-time that Einstein envisioned dissolves into chaos at the event horizon, replaced by a seething torrent of energy. This violation of general relativity's predictions is not merely academic. It signals a fundamental incompatibility between the two great theories that govern the cosmos. At the same time, the firewall hypothesis places quantum mechanics in a precarious position. While it preserves the principle of information conservation, it does so at the expense of locality. The idea that physical processes occur in specific locations in space-time, the firewall, if real, would imply that the state of the universe at the event horizon is determined not by local interactions, but by the global properties of the black hole. This non-locality challenges our intuitive understanding of cause and effect, suggesting that the universe operates according to rules we have yet to fully comprehend. Furthermore, the energy required to create a firewall is staggering. Calculations suggest that the temperature of the firewall could reach trillions of degrees, hotter than the core of any star. Such an environment would obliterate all known forms of matter, reducing them to elementary particles in an instant. The paradox created by the firewall hypothesis has sparked a fierce debate among physicists. Some argue that the hypothesis is a necessary consequence of quantum mechanics, a price worth paying to preserve the integrity of the theory. Others contend that it is an artifact of flawed assumptions, a misinterpretation of the mathematics, rather than a true reflection of reality. This divide reflects a deeper philosophical question. Is the universe governed by a single unified set of laws, or do quantum mechanics and general relativity represent distinct regimes that must be reconciled through a yet-to-be-discovered framework? The firewall paradox is not simply a problem of black holes. It is a microcosm of the larger struggle to unify the fundamental forces of nature. The search for a resolution to this paradox has led to some of the most imaginative ideas in theoretical physics. String theory, loop quantum gravity, and other approaches to quantum gravity aim to bridge the gap between the quantum and relativistic worlds. These theories propose that space-time is not a continuous fabric, but a discrete granular structure at the Planck scale. If true, the event horizon might not be a smooth boundary, but a complex network of quantum threads, capable of preserving information without the need for a destructive firewall. Other proposals suggest that the paradox arises from an incorrect application of quantum field theory in curved space-time, a limitation that could be overcome by a more complete theory. Regardless of the path forward, the firewall hypothesis has reshaped our understanding of black holes and their role in the universe. No longer can they be seen as simple, static objects defined solely by their mass, spin, and charge. Instead, they emerge as dynamic entities that interact with the quantum vacuum in ways that challenge our intuitions. The event horizon, once thought to be a mere mathematical boundary, is now a site of intense activity, where the laws of physics are pushed to their breaking point. This realization underscores the importance of black holes as laboratories for testing the limits of our theories. By studying the behavior of matter and energy in these extreme environments, we gain insights into the fundamental nature of reality. Moreover, the firewall hypothesis invites us to reconsider our place in the cosmos. If the universe is willing to sacrifice the smoothness of space-time to preserve quantum principles, it suggests that information holds a primacy we have yet to fully appreciate. This idea resonates with emerging perspectives in quantum information theory, which view the universe as a vast computational system where the storage and transmission of information are as fundamental as energy and matter. In this framework, the firewall is not a destructive anomaly, but a necessary mechanism for maintaining the coherence of the cosmic code. Such a perspective transforms our understanding of the universe from a collection of inert objects to a living, evolving network of information. As we grapple with these implications, it becomes clear that the firewall hypothesis is more than a theoretical curiosity. It is a harbinger of a new era in physics, one in which the boundaries between disciplines blur, and the pursuit of knowledge demands a synthesis of the deepest truths of the universe. The paradox it presents is not a dead end but a catalyst, pushing us to refine our theories and expand our imaginations. Whether or not firewalls ultimately exist, their very consideration has already enriched our understanding of the cosmos, reminding us that the universe is far stranger and more wondrous than we dare to imagine. While the firewall hypothesis offers a dramatic resolution to the information paradox, it is not without its critics. The idea that the event horizon is a violent, incendiary barrier seems at odds with the elegance of general relativity, which describes space-time as a seamless continuum. Many physicists, including some of the most prominent thinkers in the field, have sought alternatives that preserve both quantum mechanics and the equivalence principle. One such proposal, known as black hole complementarity, suggests that the paradox is not a problem to be resolved, but a misinterpretation of reality itself. According to this view, the information that falls into a black hole is not truly lost but encoded in the outgoing Hawking radiation, allowing an external observer to reconstruct the infalling matter's history. Simultaneously, an observer falling into the black hole experiences nothing unusual at the event horizon, consistent with Einstein's predictions. This dual perspective, though seemingly contradictory, is reconciled by recognizing that the two observers occupy fundamentally different reference frames. What one sees as a firewall, the other perceives as a tranquil descent. Black hole complementarity represents a radical departure from conventional thinking, challenging the notion that reality is objective and universal. Instead, it proposes that the universe accommodates multiple, seemingly incompatible descriptions of the same event, depending on the observer's frame of reference. This idea, inspired by the Copenhagen interpretation of quantum mechanics, suggests that the paradox is not a flaw in the theories but a feature of the universe's structure. By embracing complementarity, physicists hope to avoid the catastrophic consequences of the firewall hypothesis while preserving the integrity of both quantum mechanics and general relativity. Yet this approach is not without its own difficulties. The requirement that information be simultaneously preserved and inaccessible raises questions about the nature of reality and the limits of human knowledge. If the universe allows for such a duality, it implies that our understanding of physical law is inherently limited by the perspectives we inhabit. As we turn our attention to black hole complementarity, we enter a realm where the very definition of reality is called into question. This transition is not merely a shift in theoretical models, but a profound re-examination of the assumptions that underpin our scientific worldview. The firewall hypothesis, with its stark confrontation of opposing principles, has illuminated the chasm between quantum mechanics and general relativity. Yet it is in the exploration of alternatives, such as complementarity, that we glimpse the possibility of a deeper synthesis, a framework in which the contradictions of the past are resolved, not through compromise but through transformation. The journey continues, guided by the relentless pursuit of truth and the boundless mystery of the cosmos. At the heart of modern physics lies a profound realization. The universe may not present a single, objective truth to all observers. Instead, reality might be a tapestry woven by the threads of perception, shaped by the vantage point from which it is viewed. This notion, once dismissed as speculative, has taken center stage in the study of black holes. particularly through the concept of black hole complementarity. The idea challenges our deepest intuitions about existence, suggesting that two seemingly contradictory descriptions of the same event can both be true, at least within the framework of quantum mechanics and general relativity. From the perspective of an observer standing safely outside a black hole's event horizon, information about objects that fall in appears to be encoded in the faint glow of Hawking radiation. Yet, for an unfortunate traveler plummeting into the abyss, the journey remains smooth and uneventful, with no indication that anything has been lost to the void. These two accounts, though mutually exclusive in classical terms, do not contradict one another because no observer can experience both perspectives simultaneously. The universe, in this view, does not demand a single, definitive version of events. Instead, it accommodates multiple truths, each valid within its own frame of reference. This revelation reshapes our understanding of the cosmos, shifting the focus from an absolute observer-independent reality to one that is inherently relational. It suggests that the very fabric of existence is not a fixed backdrop against which events unfold, but rather a dynamic interplay between the observer and the observed. In the context of black holes, this means that what one person perceives as the slow, gradual emission of information in the form of radiation is, for another, an immediate and unremarkable descent into the singularity. The absence of a shared universal viewpoint eliminates the possibility of paradoxes arising from these differing narratives. Rather than seeking to reconcile them, physicists have come to accept that reality is not a singular thread, but a vast multi-dimensional weave, one that only reveals its full complexity when examined from multiple angles. This paradigm shift has far-reaching consequences, not only for our comprehension of black holes, but also for the broader quest to unify quantum mechanics and general relativity, the two pillars of modern physics. At the core of black hole complementarity lies a fundamental tenet of quantum mechanics, the principle that observation itself plays an active role in defining reality. Unlike classical physics, which assumes that physical properties exist independently of measurement, quantum theory asserts that certain aspects of a system remain undefined until they are observed. This concept is exemplified in the phenomenon of entanglement, where particles become correlated in such a way that the state of one instantaneously influences the state of another, regardless of the distance separating them. When applied to black holes, this principle takes on a striking form, revealing that the fate of information, whether it is preserved inside the event horizon or radiated outward, is not an inherent property of the black hole itself, but rather a consequence of the observer's position relative to it. Consider an external observer, stationed at a safe distance from a black hole. According to quantum field theory, the vacuum surrounding a black hole is not truly empty but teems with virtual particle pairs, constantly forming and annihilating. Occasionally, one member of a pair may fall into the black hole, while the other escapes, carrying away energy in the form of what is now known as Hawking radiation. Over time, this process leads to the gradual evaporation of the black hole, with the escaping particles encoding information about the matter that had previously fallen in. From the perspective of this distant observer, the information is not destroyed but instead slowly released into the cosmos, albeit in a scrambled and highly entangled form. This view aligns with the principles of quantum mechanics, which forbid the outright destruction of information, a rule known as unitarity. In contrast, a different picture emerges for an observer who dares to cross the event horizon. As they descend toward the singularity, they encounter no dramatic change at the boundary of the black hole. Space continues to flow around them, and the laws of physics remain consistent with those experienced in any other region of the universe. From this vantage point, the information about the infalling object is not lost, but rather carried along with the observer, embedded in the local space-time continuum. There is no sudden scrambling of data or violent interaction with a mysterious firewall, only a seamless continuation of the traveler's journey. This apparent contradiction is not a flaw in the model, but a feature of the universe's deeper structure, one that demands that both perspectives be considered equally valid. Lenny Suskind's formulation of black hole complementarity provides a framework for reconciling these two viewpoints. By recognizing that no observer can simultaneously witness both the external radiation and the internal descent, the paradox dissolves. The information is neither duplicated nor destroyed, Instead, it exists in a superposition of states, accessible to different observers in distinct ways. This insight not only resolves the long-standing conflict between quantum mechanics and general relativity, but also hints at a more profound truth, that the universe operates according to rules that transcend our conventional notions of causality and locality. In this cosmic dance of entropy and order, the very act of observation becomes a key to unlocking the mysteries of existence. The implications of black hole complementarity extend beyond the immediate realm of astrophysics, challenging some of the most deeply ingrained assumptions about the nature of reality. At its core, this principle suggests that the universe does not require a single, unified description of events. Instead, it allows for multiple observer-dependent truths to coexist without contradiction. This notion, while radical, is not entirely foreign to the foundations of quantum mechanics, where the act of measurement itself alters the state of a system. However, when applied to the extreme conditions near a black hole, it raises profound questions about the limits of knowledge and the boundaries of physical law. If two observers can experience entirely different versions of the same event, what does that say about the objectivity of reality? And if reality is fundamentally relational, what does that mean for our search for a theory of everything? One of the most striking consequences of complementarity is its potential to resolve the so-called information paradox, a long-standing problem in theoretical physics. According to general relativity, once an object crosses the event horizon of a black hole, it is lost forever, its information irretrievably swallowed by the singularity. But quantum mechanics insists that information cannot simply vanish. It must be conserved, encoded in some form that can be retrieved, however indirectly. For years, physicists struggled to reconcile these two seemingly incompatible principles, with some proposing the existence of a mysterious firewall at the event horizon, an energetic barrier that would incinerate any infalling matter, thereby preserving the integrity of quantum information. Others argued for alternative solutions, including the idea that information is somehow stored on the surface of the black hole, much like data on the two-dimensional surface of a hologram. Black hole complementarity offers a compelling resolution to this dilemma by rejecting the need for a single, absolute account of what happens to information. Instead, it embraces the idea that the external observer sees the information encoded in Hawking radiation, while the infalling observer experiences it as being carried along with them into the depths of the black hole. Crucially, there is no mechanism by which either observer can verify the other's perspective, no experimental setup that would allow an external observer to peer inside the event horizon, or a falling observer to communicate their findings after crossing it. This absence of direct verification eliminates the possibility of contradiction, allowing both descriptions to stand as equally valid within their respective frames of reference. In this sense, the paradox is not truly resolved in the traditional sense, but rather dissolved by redefining the problem itself. Yet, despite its elegance, black hole complementarity is not without its detractors. Some physicists argue that the concept violates the principle of Occam's razor, which favors simpler explanations over unnecessarily complex ones. After all, if two different versions of reality can coexist without contradiction, why should we accept the existence of multiple, irreconcilable truths rather than seek a deeper, more unified description of the universe? Critics also point out that complementarity relies on the assumption that no observer can ever access both perspectives, a condition that may not hold in all theoretical scenarios. If a future theory of quantum gravity were to provide a way for an observer to step outside the constraints of their frame of reference and witness both the external radiation and the internal descent, the entire foundation of complementarity could collapse. Despite these concerns, the idea of complementarity represents a significant step forward in the ongoing effort to unify quantum mechanics and general relativity. It suggests that the universe may not be governed by a single, all-encompassing set of rules, but rather by a hierarchy of descriptions, each applicable within specific observational contexts. In this view, the laws of physics are not absolute but conditional, adapting to the observer's position and the tools available to them. This realization has far-reaching consequences for our understanding of the cosmos, pointing toward a future in which the boundaries between subject and object, between observer and observed, blur into a more fluid and interconnected whole. As scientists continue to probe the mysteries of black holes and the nature of space-time, they may find that the answers lie not in a single definitive truth, but in the recognition that reality itself is a mosaic of perspectives, each contributing a piece to the grand puzzle of existence. If black hole complementarity challenges our understanding of reality by embracing multiple observer-dependent truths, then the next frontier of discovery may reveal an even more astonishing feature of the universe: its hidden architecture of connection. What if the cosmos is not merely a collection of isolated phenomena, but an intricate web of relationships, where even the most distant regions are bound together by unseen threads? This notion, once dismissed as mere speculation, is gaining traction in theoretical physics under the guise of a revolutionary idea: wormholes. These hypothetical tunnels through space-time, first proposed by Einstein and Rosen in 1935, suggest that black holes may not be mere endpoints of gravitational collapse, but gateways to other parts of the universe, or perhaps even other universes altogether. The concept of wormholes arises naturally from the equations of general relativity, which describe the curvature of space-time in response to mass and energy. While the mathematics allows for such structures, their stability remains a subject of intense debate. Without exotic forms of matter possessing negative energy density, wormholes would likely collapse before anything could pass through them. However, recent advancements in quantum gravity suggest that entanglement might play a crucial role in stabilizing these cosmic bridges. In particular, the idea of ERAPR proposed by physicists Juan Maldacena and Leonard Susskind suggests that entangled particles are connected by microscopic wormholes. This insight implies that the fabric of space-time itself may emerge from quantum entanglement, with wormholes acting as the physical manifestation of these deep correlations. If this hypothesis holds true, then black holes may not be isolated singularities, but nodes in an elaborate network of interconnected pathways. Information that falls into one black hole might not be lost, but instead transmitted through these quantum tunnels to another region of space-time. Such a scenario would offer a radically new perspective on the black hole information paradox, replacing the notion of information being destroyed with the idea that it is preserved and transported across the cosmic landscape. This vision of the universe as a vast, entangled web, where every black hole is linked to another through invisible corridors of space-time, opens the door to a deeper understanding of the fundamental forces that govern existence. As we venture further into the mysteries of the cosmos, the distinction between separate entities and the underlying unity of all things becomes increasingly blurred. The next chapter of exploration may reveal that the universe is not merely a collection of black holes, stars, and galaxies, but a living, breathing entity, an intricate symphony of interwoven destinies, where every action ripples across the fabric of reality in ways we have yet to comprehend. In the vast, star-strewn expanse of the universe, where galaxies spiral like whirlpools of light and black holes devour the very fabric of space-time, humanity has long grappled with two fundamental forces: the grand gravity-bound dance of celestial bodies and the strange subatomic ballet of quantum particles. For centuries, these realms seemed irreconcilable. General relativity, Einstein's magnum opus, describes the cosmos as a geometric tapestry, where massive objects warp the curvature of space-time, bending light and trapping matter within gravitational wells. Meanwhile, quantum mechanics paints a picture of a probabilistic universe, where particles exist in superpositions, tunnel through barriers, and communicate instantaneously across distances, defying classical intuition. These two pillars of modern physics have stood as separate towers, their foundations rooted in vastly different mathematical languages and philosophical frameworks. Yet, in the shadow of black holes, a place where gravity reigns supreme and quantum effects become unavoidable, these two worlds collide. The event horizon, that impenetrable boundary of a black hole, poses a paradox: what happens to information that crosses into its depths? According to quantum theory, information cannot be destroyed. Yet, according to relativity, nothing, not even light, can escape a black hole's grip. This contradiction, known as the information paradox, has haunted physicists for decades, challenging their understanding of both gravity and quantum mechanics. Enter a radical conjecture: ERAPR. Proposed by physicists Juan Maldacena and Leonard Susskind in the 21st century, RLEPR suggests a startling connection between two phenomena that seem utterly distinct. On one side lies the Einstein-Rosen bridge, a theoretical wormhole predicted by general relativity, a tunnel through spacetime that could, in principle, link distant regions of the universe. On the other side is quantum entanglement, the spooky action at a distance that Einstein himself found so unsettling, where two particles remain inextricably linked, no matter how far apart they travel. RLEPR dares to claim that these are not separate phenomena, but dual aspects of the same underlying reality. In this vision, entangled particles are connected not just by invisible threads of probability, but by physical bridges through spacetime. If true, this would not only resolve the black hole information paradox, but also hint at a deeper unity between the quantum and cosmic scales. To grasp the magnitude of this idea, imagine a universe where every entangled pair of particles is tethered by a microscopic wormhole, an unseen corridor through which information might flow. Such a notion challenges the very essence of locality, the principle that objects can only influence their immediate surroundings, and suggests that the fabric of reality is woven from connections that transcend space and time. As we delve deeper into RLEPR, we will explore how this conjecture marries the elegance of Einstein's geometry with the enigma of quantum entanglement, offering a glimpse into the universe's hidden architecture. To understand RLEPR, we must first unpack the two concepts it seeks to unify. An Einstein-Rosen bridge, or wormhole, is a solution to Einstein's equations of general relativity that suggests a shortcut between 2 points in spacetime. While such structures are theoretically possible, they are notoriously unstable, collapsing almost instantly under their own gravity unless held open by exotic matter with negative energy density, a substance not yet observed in nature. Despite their fragility, wormholes capture the imagination because they imply that spacetime is not a fixed stage, but a malleable entity, capable of folding and twisting in ways that defy everyday experience. Quantum entanglement, by contrast, operates on a radically different scale. When two particles become entangled, their properties become correlated in a way that persists, regardless of the distance separating them. For instance, if one entangled particle is measured to have a spin-up state, its partner will instantaneously exhibit a spin-down state, even if light years lie between them. This phenomenon, which Einstein famously dismissed as spooky action at a distance, has been experimentally verified countless times, yet it defies classical intuition. Entangled particles do not communicate in the traditional sense. Instead, their states are defined only when measured, and the correlation between them exists independently of spatial separation. RLEPR posits that these two phenomena are not coincidentally related, but are in fact two faces of the same coin. The conjecture draws upon the EDS-CFT correspondence, a groundbreaking framework in theoretical physics that equates a gravitational theory in a higher dimensional anti-de Sitter, EDS, space with a lower dimensional quantum field theory, CFT, without gravity. In this duality, entangled particles in the CFT correspond to wormholes in the EDS space. Thus, the entanglement of particles on one side of the duality manifests as a geometric connection in the gravitational description. Applying this to black holes, consider a pair of entangled particles. One falls into a black hole, while the other escapes as Hawking radiation. Classically, the infalling particle is lost forever, but RLEPR suggests otherwise. The entanglement between the particles creates a wormhole linking the interior of the black hole to the exterior universe. Through this bridge, the information carried by the infalling particle does not vanish but instead traverses the wormhole, emerging as correlations in the outgoing Hawking radiation. This process preserves information, sidestepping the paradox and hinting that black holes are not cosmic graveyards, but dynamic interfaces where quantum and gravitational phenomena intertwine. The mathematics underpinning RLEPR is as elegant as it is abstract. In the EDS-CFT framework, the geometry of spacetime emerges from the entanglement entropy of the boundary quantum system. When particles become entangled, their mutual information is encoded in the connectivity of the bulk spacetime. A wormhole, then, is not merely a static object, but a manifestation of quantum correlations. This perspective flips the conventional hierarchy. Rather than spacetime dictating the behavior of particles, the entanglement of particles shapes the geometry of spacetime itself. Critically, EPR does not assert that wormholes are traversable in the traditional sense. The wormholes it describes are non-traversable, meaning that no signal or traveler could pass through them from one end to the other. Instead, these bridges serve as conduits for information, preserving the causal structure of spacetime while enabling the exchange of quantum data. This distinction is vital. EPR does not violate causality or allow faster-than-light communication, but it does suggest that the universe's architecture is far more interconnected than previously imagined. If EPR holds true, its implications ripple far beyond black holes, challenging our most basic assumptions about the nature of reality. At its core, the conjecture suggests that spacetime is not a fundamental entity, but an emergent property of quantum entanglement. Just as a hologram encodes three-dimensional information on a two-dimensional surface, the universe might be a projection of entangled quantum systems operating at a deeper level. This idea aligns with the holographic principle, which posits that all the information contained within a volume of space can be represented as data on its boundary, a concept that has gained traction in studies of black holes and quantum gravity. Consider the profound consequence. If entanglement is the glue that binds spacetime, then the universe itself is a vast network of quantum correlations. Every atom, every star, and every galaxy is part of an intricate web of connections, with wormholes forming the invisible scaffolding that supports this structure. In this view, gravity is not a force acting on spacetime, but a consequence of the geometry generated by entanglement. The curvature of spacetime, once seen as the result of mass and energy, becomes a secondary effect of the entanglement entropy of quantum fields. This perspective transforms black holes from isolated singularities into nodes in a cosmic information network. The entropy of a black hole, which measures its information content, is proportional to the area of its event horizon, a hint that its interior may be encoded in the entangled Hawking radiation it emits. Through EPR, the black hole's interior is not a void but a region connected to the outside universe via a web of quantum wormholes. These bridges ensure that information is never truly lost, even as it appears to vanish behind the event horizon. Moreover, EPR opens the door to a radical interpretation of the universe's origins. If spacetime emerges from entanglement, then the Big Bang might not have been a singular event, but the sudden manifestation of a pre-existing quantum state. In this scenario, the early universe was a highly entangled quantum system, whose coherence gave rise to the classical spacetime we observe today. This idea resonates with theories of quantum cosmology, which seek to describe the universe's birth using principles of quantum mechanics. Perhaps most tantalizingly, EPR hints at a multiverse, a collection of parallel universes, connected by wormholes. If entangled particles in one universe are linked to those in another, then wormholes might span not just space but entire dimensions. This notion aligns with string theory and brane cosmology, which propose that our universe is but one membrane in a higher dimensional landscape. In such a framework, EPR suggests that entanglement could stitch together these membranes, creating a tapestry of interconnected realities. The philosophical implications are staggering. If spacetime is built from quantum correlations, then the universe is not a passive arena, but an active participatory system. Observers are not mere spectators, but integral to the unfolding of reality, their measurements shaping the geometry of the cosmos. This echoes the Copenhagen interpretation of quantum mechanics, where observation collapses a wave function into a definite state. In the context of EPR, the act of measuring entangled particles might be akin to probing the structure of spacetime itself, revealing the hidden architecture of the universe. Yet these ideas remain speculative. While EPR provides a compelling framework for reconciling quantum mechanics and general relativity, it lacks experimental confirmation. Current technology cannot create or detect quantum wormholes, nor can it probe the interior of a black hole. However, ongoing research in quantum computing and high-energy physics may one day provide indirect evidence. For instance, simulating entangled quantum systems on quantum computers could reveal patterns analogous to wormhole geometries, offering a glimpse into the conjecture's validity. As we stand at the threshold of this new understanding, the question arises, if wormholes connect entangled particles and black holes, could they also bridge entire universes? The ER of APR conjecture, with its suggestion that spacetime is woven from quantum threads, invites us to imagine a cosmos far vaster than the observable universe. If entanglement spans not just space but dimensions, then the multiverse may not be a realm of abstract speculation, but a tangible extension of quantum reality. In this vision, each universe is a node in a cosmic network, linked by wormholes that transcend our familiar notions of distance and time. What might such a multiverse look like? Some theories suggest that our universe is a single bubble in an infinite sea of others, each governed by different physical laws. Others propose that the multiverse is a fractal structure, with universes nested within universes ad infinitum. In either case, EPR offers a mechanism for connectivity, a way for information, perhaps even life, to traverse the boundaries between these realms. Could a civilization in a neighboring universe communicate with ours through quantum entanglement? Might wormholes serve as gateways to alternate realities, where the laws of physics are subtly different? These questions plunge us into the heart of cosmic mystery, where the line between science and philosophy blurs. If spacetime is emergent, if entanglement is the architect of reality, then the universe is not a static machine, but a living, evolving organism. Its deepest truths may lie not in the equations of physics, but in the act of observation itself, in the interplay between the quantum and the cosmic. As we venture further into this uncharted territory, we are reminded that the universe is not merely to be studied, it is to be experienced, a symphony of connections waiting to be understood. And so, with this contemplative lens, we turn to the next chapter, the multiverse. There we shall explore the possibility that our universe is but one note in an infinite cosmic score, each universe a distinct harmony, each wormhole a thread in the grand design. The universe has always been a realm of mystery, where the unknown stretches farther than the visible horizon. Yet, among the most enigmatic phenomena in cosmology are black holes, regions of space-time so dense that not even light can escape their gravitational pull. While they have long been regarded as cosmic sinks, devouring everything that dares to venture too close, some modern theories suggest that their true nature may be far more profound. What if instead of erasing matter and energy, black holes give rise to something entirely new? A radical hypothesis proposes that when a black hole collapses into a singularity, it does not vanish into oblivion, but rather spawns an entirely separate universe. In this view, the singularity acts as a cosmic womb, birthing a new reality with its own physical laws, time and space. If this idea holds any truth, it would fundamentally alter our understanding of the cosmos, transforming black holes from mere endpoints of stellar evolution into gateways to the infinite. At the heart of this speculation lies the multiverse theory, a framework in which our universe is just one of countless others, each born from the collapse of singularities. In this model, the fabric of reality is not a single static entity, but an ever-expanding network of universes, each emerging from the remnants of collapsed stars. These universes could possess wildly different properties, governed by distinct physical constants and forces. Some might harbor stars that burn in unfamiliar colors, planets where gravity behaves differently, or dimensions beyond our comprehension. The notion that information falling into a black hole does not disappear, but instead migrates into another universe, presents an elegant solution to one of the greatest puzzles in physics, the information paradox. According to quantum mechanics, information cannot be destroyed, yet classical general relativity suggests that anything crossing a black hole's event horizon is lost forever. If the data that vanishes into a black hole is not truly gone, but rather transported into a new universe, then the paradox dissolves, not because the law is broken, but because the law simply operates on a grander scale than we previously imagined. This perspective invites us to reconsider the nature of existence itself. If every black hole is a birthplace of new realities, then the cosmos is not merely expanding. It is perpetually giving rise to infinite possibilities. The universe is no longer a closed system, but an open, evolving tapestry, with each black hole serving as a seed for the next chapter in the story of creation. Such a vision elevates black holes from cosmic graveyards to cosmic cradles, suggesting that the end of one universe may be the beginning of another. As we peer into the abyss of these mysterious entities, we may be gazing not into destruction, but into the very essence of transformation, where the fabric of reality is rewoven in ways we have yet to fully understand. The foundation of the multiverse theory lies in the concept of eternal inflation, a cosmological model that describes the universe as an ever-expanding sea of quantum fluctuations. According to this theory, the early universe underwent a period of exponential expansion, driven by a hypothetical field known as the inflaton. While most regions of space eventually transitioned out of this high-energy state, some continue to inflate indefinitely, giving rise to an infinite number of bubble universes, each with its own unique properties. Our universe is just one such bubble, adrift in a vast cosmic foam of other universes, each born from the same primordial energy, but shaped by different physical laws. Within this framework, the emergence of new universes is not a rare occurrence, but a continuous process, with each bubble forming and evolving independently. It is in this context that black holes take on an unexpected role, not as mere cosmic voids, but as potential gateways to these nascent universes. Black holes, particularly supermassive ones, found at the centers of galaxies, are among the most extreme objects in the universe. Their immense gravitational pull warps space-time so drastically that nothing, not even light, can escape once it crosses the event horizon. However, recent theoretical developments suggest that under certain conditions, a black hole may not simply consume matter, but instead pinch off a region of space-time, isolating it from the rest of the universe. This process, akin to a cellular division, could lead to the formation of a baby universe, an independent reality enclosed within the black hole's event horizon. In this scenario, the collapsing singularity at the heart of a black hole does not reach infinite density, as classical general relativity predicts, but instead triggers a new phase of inflation, giving rise to a self-contained cosmos. Just as our universe may have originated from a quantum fluctuation during the early inflationary epoch, a black hole could serve as a cosmic catalyst, birthing a universe of its own. The implications of this idea extend beyond the mere creation of new universes. If information that falls into a black hole is not destroyed, but instead carried into a newly formed reality, then the fundamental principle of quantum unitarity, whereby information is preserved over time, remains intact. In traditional models of black hole evaporation, proposed by Stephen Hawking, the information paradox arises because the outgoing Hawking radiation appears to contain no imprint of the material that had fallen in. However, if the data is not truly lost, but rather transported into another universe, then the paradox dissolves. From the perspective of the parent universe, the information may seem irretrievable, but from a broader viewpoint encompassing the entire multiverse, it is simply relocated. This perspective shifts the paradox from a local inconsistency to a universal harmony, where the laws of physics remain consistent across all realities. Such a model also opens the door to a more profound understanding of the nature of time and causality. In the traditional view, a black hole represents the end of a timeline, a point where all matter and energy are compressed into a singularity, beyond which no further events occur. But if a black hole instead gives rise to a new universe, then it becomes a bridge between timelines, connecting the end of one reality to the beginning of another. This raises fascinating questions about the continuity of existence and whether there might be echoes of our own universe in the fabric of distant worlds. Could the laws governing our cosmos have been inherited from a previous universe? Might the patterns we observe in the distribution of galaxies and cosmic microwave background radiation be imprints left behind by an earlier reality? These questions, though speculative, invite us to consider that the universe may be far more interconnected than we have traditionally assumed. If every black hole births a new universe, the implications for our understanding of physics, and indeed of reality itself, are profound. At the core of this idea is a radical reimagining of the information paradox. Instead of a local contradiction, it transforms into a universal enigma. The paradox, which arises from the tension between general relativity and quantum mechanics, is no longer confined to the immediate vicinity of a black hole. Rather, it becomes a question of how information is distributed across the vast expanse of the multiverse. In this framework, the data that disappears into a black hole is not truly lost. It is merely shifted into another realm, where it continues to exist under different physical conditions. This shift reframes the paradox not as a failure of either theory, but as an indication that our current models are incomplete in their ability to describe the full scope of reality. The universe, it seems, is not a closed system, but an open one, where information flows across boundaries that we are only beginning to comprehend. This perspective challenges the anthropocentric view of the cosmos, forcing us to confront the possibility that our universe is but one thread in an infinite tapestry of existence. If black holes serve as cosmic gateways, then the very act of observation of measuring the properties of the universe may be inherently limited. We can never hope to access the information that has been transported into another universe, nor can we determine the nature of the universes that may have given rise to ours. This realization introduces a humbling sense of limitation, yet it also opens the door to a deeper appreciation of the universe's complexity. The idea that information is not destroyed but transformed invites a paradigm shift in how we perceive causality and continuity. What if the laws of physics we observe are not absolute, but contingent on the specific conditions of our universe? What if the constants that define our reality, the speed of light, the strength of gravity, the charge of the electron, are simply the result of the particular history of our cosmic bubble? Such questions suggest that the multiverse is not just a theoretical construct, but a lens through which we might begin to understand the very nature of existence. From a philosophical standpoint, the multiverse theory compels us to grapple with the implications of a reality that is not only vast but also deeply interconnected. If every black hole is a portal to a new universe, then the boundaries we perceive between past, present, and future may be far less rigid than we assume. The idea that information persists across universes raises intriguing possibilities about the continuity of consciousness and the nature of time. Could there be echoes of our own universe in the fabric of distant realities, manifesting as subtle imprints or patterns? And if so, what does this imply about the possibility of communication or even travel between these universes? While such ideas remain firmly in the realm of speculation, they underscore the profound implications of the multiverse theory for our understanding of the cosmos. However, the notion that black holes give rise to new universes also highlights the challenges of verifying such a theory. Unlike other scientific hypotheses, which can be tested through experiments or observations, the multiverse remains largely inaccessible to empirical verification. The universes born from black holes, if they exist at all, lie beyond the reach of our instruments, hidden within the event horizons of these enigmatic objects. This raises difficult questions about the nature of scientific inquiry itself. Can a theory that cannot be directly observed still hold value? Does the elegance of a mathematical framework outweigh the absence of empirical evidence? These questions are not new, but they take on added urgency in the context of the multiverse. The inability to test the theory directly does not diminish its significance. Rather, it underscores the importance of exploring the boundaries of our knowledge and embracing the unknown. Ultimately, the multiverse theory offers a vision of the cosmos that is both awe-inspiring and humbling. It invites us to consider that the universe is not a finite, closed system, but an infinite, evolving web of realities, each connected to the next by the enigmatic forces of gravity and quantum mechanics. This perspective shifts our understanding of the universe from one of isolation to one of interconnectedness, where the fate of one universe is inextricably linked to the possibilities of others. As we contemplate the implications of this theory, we are reminded that the universe is not merely a place to be explored. It is a mystery to be unraveled, a story whose ending we have yet to write. Yet, while the multiverse theory offers a grand and elegant solution to the information paradox. It remains an untestable hypothesis, stretching the limits of empirical science. Perhaps there is another way to reconcile the apparent contradiction between general relativity and to the holographic principle, a revolutionary idea that suggests the universe is not a three-dimensional volume, but rather a two-dimensional projection encoded on its boundary. This radical concept, rooted in string theory and black hole thermodynamics, posits that all the information contained within a region of space can be represented as a surface, a kind of cosmic film upon which the entire universe plays out. If this principle holds true, then the information that appears to vanish into a black hole is not lost, but instead imprinted on the event horizon, preserving it in a manner consistent with quantum mechanics. The holographic principle emerged from the study of black hole entropy, a measure of the amount of information they contain. In the 1970s, Jacob Bekenstein and Stephen Hawking demonstrated that black holes have entropy proportional to the area of their event horizon, rather than their volume. This was a startling revelation, as it suggested that the maximum amount of information that can exist within a given space is determined not by its size, but by its surface area. This insight led to the development of the ADS/CFT correspondence, a mathematical framework that equates a gravitational theory in a higher dimensional space with a quantum field theory on its lower dimensional boundary. In this model, the universe is akin to a hologram, where the three-dimensional world we experience is a projection of information stored on a two-dimensional surface. If this principle applies to our universe, then the information that falls into a black hole is not destroyed, but rather encoded on its event horizon in a form we have yet to fully understand. This perspective provides an alternative resolution to the information paradox, one that does not invoke the existence of baby universes or parallel realities. Instead, it suggests that the information is never truly lost. It is simply transformed, much like light reflected on the surface of a mirror. By viewing the universe as a holographic projection, we may be able to preserve the principle of unitarity without requiring the existence of multiple universes. This idea, though still under investigation, offers a compelling path forward in the quest to unify general relativity and quantum mechanics. As we continue to probe the nature of black holes and the fabric of space-time, we may find that the answers to our deepest questions lie not in the vast expanse of the multiverse, but in the intricate patterns etched onto the surface of reality itself. In the vast tapestry of existence, where stars burn like ancient sentinels and galaxies spiral in silent choreography, lies a riddle that defies intuition. What if the three-dimensional world we inhabit, the one we touch, see and navigate, is merely a shadow cast by something far more profound? Picture, if you will, a hologram, a flat, two-dimensional surface etched with intricate patterns that, when illuminated, project a lifelike, three-dimensional image. The holographic principle posits that our universe operates under a similar principle. Every particle, every star, every nebula, and even the voids between galaxies might be encoded on a distant, unseen boundary, a cosmic membrane that encases all of space. This notion, at once humbling and exhilarating, challenges the very fabric of our understanding. It suggests that the universe is not a physical construct of matter and energy, but a projection of information, a grand simulation where depth is an illusion and truth resides in the flatness of a surface. Consider the event horizon of a black hole, that enigmatic boundary from which nothing, not even light, can escape. To an outside observer, it appears as a simple two-dimensional shell, yet within, it harbors secrets that defy classical physics. When an object falls into a black hole, its matter seems to vanish, swallowed by the abyss. But where does the information about that object go? The holographic principle offers a daring answer. It is imprinted on the event horizon itself, stored as a kind of cosmic ledger. This idea, born from the interplay of quantum mechanics and general relativity, hints at a deeper unity between forces long thought incompatible. If true, it would mean that the universe is not a three-dimensional stage, but a two-dimensional screen, and the drama of existence is played out in a way that transcends our sensory perceptions. This revelation invites us to reconsider the nature of reality. Are we inhabitants of a physical cosmos, or are we like the characters in a holographic play, unaware that our movements are dictated by a code etched on a distant plane. The question is not merely academic. It strikes at the heart of what it means to exist. If the universe is a hologram, then space, time, and matter may be emergent phenomena, byproducts of a more fundamental layer of information. Such a perspective transforms our understanding of the cosmos from a materialistic framework to an informational one, where the essence of reality is not substance but data, and the laws of physics are algorithms that compute the unfolding of the universe. To grasp the holographic principle, one must first grapple with the strange physics of black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking unveiled a startling truth. Black holes possess entropy, a measure of disorder or information content. Their work revealed that the entropy of a black hole is proportional not to its volume, as one might expect, but to the surface area of its event horizon. This discovery, encapsulated in the Bekenstein-Hawking entropy formula, SKA4LP Cabrad, where S is entropy, K is Boltzmann's constant, A is the area of the event horizon, and LP is the Planck length, became a cornerstone of the holographic principle. The formula implies that the maximum amount of information that can be contained within a region of space is determined by the size of its boundary, not its interior. This is profoundly counterintuitive. Imagine filling a room with books. Classically, the number of books depends on the room's volume. Yet, according to the holographic principle, the number of books is instead limited by the area of the walls. This insight led to the radical proposition that space-time itself may be emergent, a secondary phenomenon arising from a more fundamental, two-dimensional substrate. Just as a hologram's three-dimensional image emerges from interference patterns on a flat surface, the universe's apparent three dimensions might arise from a lower-dimensional reality. In this view, gravity is not a fundamental force, but an emergent property, akin to the statistical behavior of entropy. When particles interact or masses attract one another, their movements are not governed by Newton's laws or Einstein's equations in isolation, but by the flow of information across the holographic boundary. The gravitational pull we feel could be a macroscopic manifestation of microscopic entropy changes on the surface of the cosmos. The mathematics of string theory and quantum field theory have further refined this idea. In particular, the ADS-CFT correspondence, a conjectured duality between a gravitational theory in a higher dimensional anti-de Sitter space and a quantum field theory on its boundary, provides a concrete framework for exploring the holographic principle. Though abstract and mathematically complex, this correspondence demonstrates that a universe with gravity can be fully described by a theory without gravity, existing on a lower dimensional surface. This duality has profound implications. It suggests that the universe's complexity, including its gravitational interactions, can be reduced to simpler, non-gravitational equations operating on a boundary. The universe, in essence, becomes a computational system, where the rules of physics are encoded in a language of information, and the three-dimensional world we perceive is a dynamic projection of that code. The ADS-SCFT correspondence, proposed by Juan Maldacena in 1997, stands as one of the most revolutionary breakthroughs in theoretical physics. It posits a precise equivalence between a theory of quantum gravity in a higher dimensional anti-de Sitter ADS space and a conformal field theory CFT on its lower dimensional boundary. While ADS spaces are not direct models of our universe, which appears to have positive curvature and dark energy, the correspondence has offered unprecedented insights into the nature of quantum gravity. By translating problems in a gravitational context into solvable equations in a non-gravitational framework, physicists have made strides in understanding phenomena such as black hole entropy, quantum entanglement, and even the behavior of quark-gluon plasmas in particle accelerators. The correspondence does not merely describe a mathematical curiosity. It hints at a universal principle that transcends specific cosmological models. If the ADS-CFT duality holds for our universe, it would imply that the cosmos is a hologram, with all its complexities reducible to the interactions of a two-dimensional quantum field. One of the most profound implications of the holographic principle is its potential resolution of the black hole information paradox. For decades, physicists debated whether information entering a black hole is truly destroyed or merely hidden. According to quantum mechanics, information cannot be lost, yet general relativity suggests that anything crossing an event horizon is irretrievably erased. The holographic principle reconciles these contradictions by asserting that information is never lost, it is simply encoded on the event horizon. As a black hole evaporates via Hawking radiation, this information is gradually released, though the exact mechanism remains a subject of intense study. The holographic model treats the event horizon as a kind of cosmic hard drive, storing the data of everything it consumes. This idea not only salvages the principles of quantum mechanics, but also reinforces the notion that the universe operates as an information processing system, where every interaction is a computation. Beyond black holes, the holographic principle challenges our perception of space-time itself. If the universe is a projection from a two-dimensional surface, then space and time may not be fundamental entities but emergent properties. This perspective aligns with the growing trend in physics toward viewing reality through the lens of information theory. In this framework, the fabric of space-time is akin to a software-generated interface, a user-friendly abstraction that simplifies the raw data of the cosmos. The quantum fluctuations that give rise to particles, the gravitational waves that ripple through the vacuum, and the expansion of the universe, all emerge from the underlying code of the holographic boundary. Such a view dissolves the dichotomy between observer and observed, suggesting that consciousness itself may be intertwined with the computational processes that govern reality. Philosophically, the holographic principle compels us to confront the nature of existence. If the universe is a hologram, then our experiences, our sense of depth, motion, and causality are constructs derived from a more fundamental, flat reality. This raises existential questions. Is there a real universe beyond the projection? Or is the projection all that exists? Could multiple observers perceive different holograms, each valid within their own frame of reference? These queries echo the age-old debate between idealism and materialism, now reframed in the language of modern physics. The holographic principle does not provide answers but illuminates new paths for inquiry, inviting us to reimagine the cosmos as a living, evolving information system rather than a static machine. If the universe is a hologram, then our understanding of space, time, and matter must be redefined. The notion that reality is fundamentally two-dimensional, with the third dimension emerging as a perceptual artifact, shatters conventional assumptions. Yet this is only the beginning. The holographic principle opens a portal to deeper mysteries. What is the nature of the boundary that encodes the universe? Is it a physical surface, or is it an abstract, mathematical construct? And if information is the bedrock of existence, how does it give rise to the tangible world we inhabit? These questions lead us to the frontier of quantum gravity and the quest for a unified theory of everything. They compel us to explore not only the structure of space-time, but the very origins of reality itself. As we stand at this threshold, we realize that the universe may be far stranger than we dare imagine. The holographic principle is but one thread in the tapestry of cosmic truths, woven from the threads of entropy, information, and duality. In the next segment, we will delve into the implications of this principle for the nature of consciousness and the possibility that the universe is not merely a hologram, but a conscious entity, an infinite self-aware algorithm, computing its own existence. Until then, let us carry forward the wonder of a cosmos that defies the limits of our senses, where every star and shadow whispers the secrets of a deeper, more interconnected reality. At the heart of modern physics lies a profound realization. The universe may not be composed of matter in the way we traditionally perceive it. Instead, some of the most groundbreaking theories suggest that reality itself is woven from the fabric of information. This revolutionary concept, first proposed by physicist John Archibald Wheeler in the mid-20th century, has since become one of the most compelling frameworks for understanding the nature of existence. Known as it from bit, Wheeler's idea posits that all physical entities, particles, forces, and even the very geometry of space and time emerge from the exchange and processing of information. In this view, The universe is not merely a collection of material objects, but an immense computational system where the fundamental building blocks are not atoms or energy, but bits of data. To grasp the significance of this paradigm shift, one must first step beyond the familiar notion of matter as the primary substance of reality. In classical physics, the world was described as a vast mechanism governed by deterministic laws, where objects interacted according to fixed rules of motion and force. However, the rise of quantum mechanics in the early 20th century challenged this perspective, revealing a universe where particles could exist in multiple states simultaneously, and where the mere act of observation influenced outcomes. This inherent uncertainty at the quantum level hinted at something deeper, a hidden layer of reality that defied conventional materialistic explanations. It was within this context that John Wheeler introduced his provocative hypothesis: perhaps the universe is not constructed from matter, but from information, with every event and interaction encoding a message in the cosmic ledger of existence. Wheeler's vision extended beyond abstract speculation. He suggested that black holes, those enigmatic gravitational behemoths, might serve as cosmic hard drives, storing vast amounts of information within their event horizons. This insight laid the groundwork for later developments in quantum information theory, which now explores how information behaves under extreme conditions, such as those found near a singularity. According to this framework, the entropy of a black hole, a measure of its internal disorder, is directly related to the amount of information it contains. As a black hole evaporates through a process known as Hawking radiation, it does not simply vanish. Rather, it releases its stored information in a form that, if properly decoded, could reconstruct the original data that once crossed its boundary. This revelation has led physicists to reconsider the very fabric of space-time, suggesting that what we perceive as gravity and spatial dimensions may arise from more fundamental informational processes. The implications of this perspective are staggering. If the universe operates like a vast computational system, then the emergence of complexity from elementary particles to galaxies may be the result of an underlying logic that governs the flow of information. This idea transforms our understanding of reality, shifting the focus from matter and energy to the dynamic interplay of data. It invites us to imagine the cosmos not as a lifeless machine, but as a living, evolving entity, where every moment is a computation shaping the next. In this grand cosmic framework, the universe is not just a place, it is a process, a continuous unfolding of information that gives rise to all that we know and experience. At the core of the it from bit framework lies a fundamental truth. Every interaction in the universe is, at its essence, an exchange of information. From the simplest quantum fluctuations to the most complex structures in the cosmos, the flow of data shapes the fabric of reality. Consider the phenomenon of quantum entanglement, where two particles become correlated in such a way that the state of one instantly influences the other, regardless of the distance separating them. This instantaneous connection, which Einstein famously referred to as spooky action at a distance, is not a violation of causality, but rather a manifestation of the deep interconnectivity of information in the quantum realm. When particles interact, they do not merely exert forces upon one another. They share and process information, encoding the history of their interactions into the quantum state that defines their behavior. This principle extends beyond the microscopic world of quantum mechanics and into the grand scale of astrophysical phenomena. Black holes, long considered the ultimate sinkholes of the universe, have revealed themselves to be far more than just regions of space-time from which nothing can escape. They are, in fact, information processes of unparalleled complexity. According to the Wittgenstein-Hawking formula, the entropy of a black hole is proportional to the area of its event horizon, rather than its volume, a striking departure from classical thermodynamics. This suggests that the information contained within a black hole is not distributed uniformly throughout its interior, but rather encoded on its surface, an idea that forms the foundation of the holographic principle. Just as a two-dimensional hologram can contain a three-dimensional image, the event horizon of a black hole may store all the information about its contents, preserving the data even as the object itself undergoes transformation. As a black hole evaporates over eons via Hawking radiation, it does not simply vanish into oblivion. Instead, it releases this stored information in the form of quantum correlations embedded in the emitted particles. Theoretical physicist Stephen Hawking initially proposed that this radiation would be random and unstructured, implying that the information within the black hole would be lost forever. However, this conclusion conflicts with the principles of quantum mechanics, which demand that information must be conserved. This paradox, known as the black hole information paradox, has driven decades of research into the nature of information in the universe. Recent insights from quantum information theory suggest that the radiation emitted by a black hole carries subtle correlations that preserve the integrity of the original data. These correlations, though seemingly imperceptible against the backdrop of cosmic noise, represent a vast, encrypted record of the black hole's internal state. Deciphering this information remains one of the greatest challenges in theoretical physics, as it requires a complete understanding of how quantum mechanics and general relativity merge in the extreme environment of a black hole. This intricate relationship between information and reality becomes even more apparent when we consider the broader implications of the it-from-bit hypothesis. If all physical phenomena ultimately stem from the exchange of information, then the very structure of space-time may not be fundamental, but rather an emergent property of these informational interactions. In this view, gravity is not a force acting upon mass, but an expression of the constraints imposed by the conservation and distribution of information. The curvature of space-time, the bending of light around massive objects, and the expansion of the universe itself may all be manifestations of the same underlying logic that governs the flow of data across the cosmos. This perspective reframes our understanding of the universe, shifting the focus from material substances to the dynamic processes that shape them. The realization that the universe operates as a vast computational system opens new avenues for exploring the nature of existence. If information is the fundamental currency of reality, then the evolution of the cosmos may be akin to a cosmic computation, where each moment builds upon the previous one in an intricate dance of cause and effect. This idea aligns with the growing field of quantum computing, which seeks to harness the power of information processing to solve problems beyond the reach of classical computers. In both cases, the manipulation of information determines the outcome of complex systems, whether it be the simulation of quantum states or the prediction of cosmic events. By embracing this perspective, we begin to see the universe not as a static collection of objects, but as a dynamic, ever-evolving network of information, where every interaction contributes to the unfolding story of existence. The realization that the universe functions as a vast computational system reshapes our understanding of existence in ways that challenge both scientific and philosophical paradigms. If all phenomena, matter, energy, space, and time, arise from the processing of information, then the cosmos itself may be best understood not as a passive stage for physical events, but as an active participant in a grand, self-referential process of computation. This perspective reframes the age-old question of what constitutes reality. Rather than being a fixed objective structure waiting to be observed, the universe becomes an evolving algorithm where every interaction is a step in an ongoing calculation that determines the next state of existence. In this view, the emergence of complexity ranging from subatomic particles to galaxies results from the recursive application of fundamental informational rules. The cosmos is not merely governed by laws, it is a law in itself, a self-contained system of information processing that generates the patterns we observe. One of the most profound implications of this framework is the redefinition of space-time and gravity. Traditionally, general relativity describes gravity as the curvature of space-time caused by the presence of mass and energy. However, in the context of it-from-bit, gravity may instead emerge as a consequence of the constraints imposed by information conservation. This idea draws from the concept of entropic gravity, which posits that gravity is not a fundamental force, but rather an emergent phenomenon resulting from the statistical behavior of information. In this model, the force of gravity arises from the tendency of systems to maximize entropy, the measure of disorder or information content, by redistributing energy across space. The curvature of space-time, then, is not an intrinsic property of the universe, but an expression of the way information is organized and processed within it. This perspective offers a new lens through which to interpret gravitational effect, suggesting that the familiar pull of gravity is in essence a consequence of the universe's effort to maintain equilibrium in its informational state. Beyond space-time and gravity, the computational nature of the universe also raises intriguing questions about the origins of complexity. If the cosmos operates as an information processing system, then the emergence of intricate structures such as stars, planets, and life itself must be understood in terms of algorithmic evolution. Just as simple rules in cellular automata can give rise to complex patterns, the universe may follow similar principles where basic informational interactions lead to the spontaneous formation of higher-order structures. This idea resonates with the concept of self-organized creatility, a phenomenon observed in systems ranging from sandpiles to neural networks, where small perturbations trigger cascading effects that shape the overall structure of the system. In this context, the universe is not a passive arena for cosmic events, but an active, self-regulating system that continuously refines its informational architecture to produce the rich diversity of phenomena we observe. The implications of this perspective extend into the domain of quantum mechanics, where the role of information becomes even more pronounced. The wave function, a mathematical description of a quantum system's state, encodes probabilities rather than definite values, reflecting the inherent uncertainty of quantum measurements. However, within the framework of it from bit, this uncertainty may not be a limitation of our knowledge, but rather a fundamental aspect of reality itself. The probabilistic nature of quantum mechanics suggests that the universe is not deterministic in the classical sense. Instead, it operates through a process of information selection, where the act of measurement collapses potential possibilities into a single outcome. This idea aligns with the Copenhagen interpretation of quantum mechanics, which emphasizes the role of the observer in determining the final state of a system. Yet, it also raises deeper questions about the nature of observation and the boundaries between the observer and the observed. If information is the fundamental substance of reality, then the act of observation may not be a passive process, but an integral part of the universe's computational framework. Perhaps the most profound consequence of the it from bit hypothesis is its challenge to the traditional dichotomy between matter and information. In classical physics, matter is seen as the primary substance of the universe, with energy and forces serving as secondary descriptors of its behavior. However, the idea that reality is fundamentally informational shifts this hierarchy, placing information at the base of all existence. This shift has far-reaching consequences, particularly in the fields of cosmology and quantum gravity, where researchers seek to reconcile the macroscopic laws of general relativity with the microscopic rules of quantum mechanics. If the universe is ultimately an information processing system, then the search for a unified theory of physics may not require the discovery of new fundamental particles or forces, but rather a deeper understanding of how information is structured and processed at the most fundamental levels. Moreover, this perspective invites a re-evaluation of the role of computation in the natural world. While quantum computing represents a human attempt to harness the power of information processing, the universe itself may already be performing computations on an unimaginable scale. Every particle interaction, every cosmic event, and every quantum fluctuation contributes to an ongoing calculation that defines the state of the universe at any given moment. This idea aligns with the concept of digital physics, which proposes that the universe operates like a vast computer program, executing instructions encoded in the laws of nature. If this is true, then the cosmos is not merely a physical system governed by external laws, but an autonomous computational process, where the rules of physics emerge from the logic of information processing itself. Ultimately, the notion that the universe is a computational system challenges us to rethink our place within it. If reality is shaped by the flow of information, then the emergence of consciousness and intelligence may not be anomalies but inevitable outcomes of the universe's self-organizing tendencies. Life in this view is not an accidental byproduct of cosmic processes, but a natural progression in the universe's evolution toward greater complexity and self-awareness. This perspective transforms our understanding of existence, positioning humanity not as passive observers of an indifferent cosmos, but as participants in an ongoing computational process that continues to unfold across time and space. If the universe is fundamentally a vast computational system, then the role of the observer becomes a central question in understanding the nature of reality. In classical physics, the observer is often treated as an external entity, a passive recorder of events occurring independently of perception. However, quantum mechanics has shown that this separation is not as clear-cut as once believed. The act of measurement itself appears to influence the outcome of quantum experiments, a phenomenon encapsulated in the famous double-slit experiment. When particles such as photons are observed, their wave-like behavior collapses into a localized particle state, suggesting that the very act of observation alters the system being measured. This raises a profound question. If the universe is built upon information, and if the processing of that information defines reality, then what is the role of the observer in this grand cosmic computation? Is the observer a mere bystander, or is the observer an essential component of the system itself? John Wheeler, the originator of the it-from-bit hypothesis, explored this question in depth, proposing that the universe may be participatory in nature. His thought experiment, known as the delayed choice experiment, demonstrated that the decision to observe a quantum event can retroactively determine the nature of that event, even after the initial interaction has occurred. This suggests that the act of observation does not merely reveal an existing state of affairs, but actively participates in shaping the outcome. If this principle holds at a fundamental level, then the universe may not be a fixed, preordained structure, but a dynamic, self-referential system in which the observer plays an integral role. This idea challenges the traditional notion of an objective reality independent of conscious experience, suggesting instead that reality is, in some sense, co-created through the process of observation. The implications of this perspective extend beyond theoretical physics and into the realm of philosophy and consciousness studies. If the observer is not an external agent, but an intrinsic part of the information processing framework that defines the universe, then the nature of consciousness itself becomes a critical factor in understanding the cosmos. Some interpretations of quantum mechanics, such as the von Neumann-Wigner interpretation, propose that consciousness is necessary to collapse the quantum wave function, effectively bringing reality into existence. While this view remains controversial, it highlights the deep interplay between information and awareness. If the universe is fundamentally informational, then consciousness may not be an emergent property of biological systems, but a fundamental aspect of the cosmic code itself. This line of reasoning leads to an even more radical possibility, that the universe is not only governed by information, but is, in some sense, aware of itself. The idea that the cosmos may possess a form of self-awareness or intrinsic intelligence is not new. It echoes ancient philosophies that viewed the universe as a living, conscious entity. In the context of modern physics, this perspective takes on a new dimension. If the universe operates as a computational system, then the emergence of consciousness may be an inevitable consequence of sufficiently complex information processing. Just as the human brain gives rise to subjective experience through the organization of neural activity, the universe itself may develop a form of self-awareness through the intricate web of quantum correlations and informational interactions. This brings us to the threshold of a new frontier in our understanding of existence. If the universe is a self-referential computational system, and if consciousness is an intrinsic part of that system, then the distinction between the observer and the observed may dissolve entirely. In such a framework, reality is not a fixed backdrop onto which events unfold, but an interactive, participatory process in which every act of observation contributes to the ongoing evolution of the cosmos. This perspective transforms our understanding of the universe, positioning humanity not as isolated observers of an indifferent cosmos, but as active participants in the great cosmic dialogue of information and awareness. As we stand at the intersection of physics, information theory, and consciousness, we are confronted with one of the greatest mysteries of all, the nature of the observer. What is it that allows us to perceive the universe, to question its workings, and to seek meaning within its vast expanse? Is the observer an emergent phenomenon arising from the complexity of information processing, or is the observer a fundamental element woven into the very fabric of reality? The answers to these questions may lie not only in the equations of quantum mechanics or the algorithms of information theory, but in the very essence of our own consciousness. And as we continue to explore the depths of the cosmos, we may find that the key to understanding the universe lies not in the stars above, but in the awareness that gazes upon them. In the vast expanse of the cosmos, where galaxies spiral in silent majesty and stars forge the elements that compose our very being, a profound question lingers. Does observation shape reality itself? At the heart of quantum mechanics lies a principle that defies classical intuition, the notion that a particle exists in multiple states simultaneously until it is observed. This phenomenon, known as superposition, suggests that the act of measurement is not merely a passive recording of pre-existing properties, but an active process that collapses a wave of possibilities into a single outcome. If this is true, then the observer becomes an integral part of the fabric of existence, a participant in the unfolding of the universe rather than a mere spectator. This idea takes on cosmic significance when applied to the enigmatic realm of black holes. These celestial behemoths, with their immense gravitational pull and event horizons beyond which nothing can escape, have long been a focal point for physicists seeking to reconcile general relativity with quantum mechanics. The black hole information paradox, first proposed by Stephen Hawking, questions what happens to the information contained within matter that falls into a black hole. According to Hawking's calculations, black holes emit radiation, a process now known as Hawking radiation, which gradually causes them to evaporate over time. Yet this raises a troubling implication. If a black hole disappears entirely, does the information it once held vanish with it? Such a scenario would violate a fundamental tenet of quantum mechanics, which holds that information cannot be destroyed. One possible resolution to this paradox hinges on the role of the observer. If the Copenhagen interpretation of quantum mechanics is correct, that is, if observation is required to collapse a quantum state, then perhaps information is not truly lost until it is measured. In this view, the fate of data within a black hole remains uncertain until an external observer has access to the Hawking radiation it emits. Until that moment, the information may remain in a suspended state of potentiality, neither fully preserved nor erased. This perspective transforms the black hole from a mere cosmic sinkhole into a dynamic participant in a grander quantum interplay, where the boundary between observer and observed blurs into the infinite. As we contemplate this intricate dance between physics and perception, we find ourselves drawn toward a deeper mystery. Could consciousness itself be the ultimate observer, shaping the very reality it seeks to understand? If so, then the universe is not only governed by the laws of physics, but also by the presence of minds that seek to unravel its secrets. This realization invites us to consider the profound interconnection between the cosmos and those who study it, setting the stage for a deeper exploration of the role of the observer in shaping the fundamental nature of reality. At the core of quantum mechanics lies the Copenhagen interpretation, a foundational framework that reshapes our understanding of reality. This interpretation posits that quantum systems do not possess definite properties until they are observed. Instead, particles exist in a superposition of all possible states, described by a mathematical entity known as the wave function. This wave function encapsulates the probabilities of various outcomes, but it is only upon measurement that the system collapses into a specific state. The act of observation, therefore, is not a passive act of acquiring information, but a transformative event that alters the system itself. This principle challenges the classical notion of an objective reality, independent of observers, suggesting instead that reality is, in some way, contingent upon the act of measurement. When applied to the realm of black holes, this concept introduces a fascinating twist to the information paradox. Black holes represent extreme environments where the laws of physics as well regardless of distance. In the context of black holes, this entanglement could mean that the information about the matter that fell into the black hole is encoded in the Hawking radiation that escapes. Thus, the act of observing this radiation could potentially reveal the information that was once thought to be lost. This perspective aligns with the idea that the information is preserved, albeit in a form that may not be immediately accessible until an observer intervenes. Moreover, this interpretation raises intriguing questions about the nature of time and causality. If the act of observation is essential in determining the state of a quantum system, then the timeline of events surrounding a black hole may be influenced by the timing of observations. For instance, the moment at which an observer measures the Hawking radiation could determine whether the information is deemed to have been lost or preserved. This temporal dimension adds another layer of complexity to the information paradox, suggesting that the universe operates under a set of rules that are not only deterministic but also deeply intertwined with the conscious act of observation. Recent advancements in theoretical physics have begun to explore these ideas further, with some researchers proposing that the information paradox may be resolved through a combination of quantum mechanics and general relativity. Theoretical models suggest that the information is not actually lost, but rather transformed into a highly complex state that is not easily retrievable. This transformation could imply that the information is encoded in the correlations between the emitted Hawking radiation and the remaining black hole, preserving it in a manner that is consistent with the principles of quantum mechanics. As scientists delve deeper into these concepts, they are increasingly recognizing the significance of the observer in the grand narrative of the universe. The Copenhagen interpretation serves as a reminder that our understanding of reality is inherently linked to our methods of observation. By acknowledging the role of the observer, we open the door to new possibilities for reconciling the seemingly irreconcilable aspects of quantum mechanics and general relativity. In this light, the study of black holes becomes not just a quest for answers about the nature of space and time, but also a profound exploration of our place within the cosmos and the responsibilities that come with the power to observe. As we delve deeper into the implications of the observer's role in shaping reality, we encounter a philosophical conundrum that transcends the boundaries of physics. Does the universe itself require conscious observers to manifest its properties? This idea, though speculative, invites a profound reconsideration of our place in the cosmos. If the Copenhagen interpretation holds any truth, if observation is indeed the mechanism by which quantum possibilities collapse into tangible outcomes, then the presence of consciousness becomes not merely incidental, but essential to the very structure of reality. This notion challenges the conventional materialist view, which posits that the universe operates independently of observers, governed solely by impersonal physical laws. Instead, it suggests that reality is, in some fundamental way, participatory, shaped by the act of perceiving it. This perspective raises unsettling yet compelling questions about the nature of existence. If consciousness is the ultimate observer, then what happens to the unobserved parts of the universe? Do they remain in a state of quantum flux, existing as probabilities rather than actualities? Could entire regions of space, devoid of conscious beings, remain in a suspended state of potentiality? These questions push the boundaries of our understanding, hinting at a cosmos that is not merely a static backdrop for life, but an active participant in its own unfolding. The universe, in this view, is not a clockwork mechanism ticking away in isolation, but a dynamic interplay between the observed and the observer, where meaning and structure emerge only through the lens of conscious awareness. This line of thought finds echoes in the writings of philosophers and physicists alike. The renowned mathematician and physicist John von Neumann speculated that the mind of the observer plays a pivotal role in the collapse of the wave function, suggesting that consciousness is not an epiphenomenon, but an intrinsic component of the quantum process. Similarly, the physicist Eugene Wigner argued that the act of observation cannot be explained solely in terms of physical interactions. Rather, it necessitates the involvement of a conscious entity. These perspectives challenge the reductionist impulse to explain everything in terms of material causes, suggesting instead that consciousness may be a fundamental aspect of reality, woven into the very fabric of the cosmos. Yet this idea is not without its critics. Many physicists and philosophers reject the notion that consciousness is required for the collapse of quantum states, arguing that such an interpretation introduces unnecessary subjectivity into the scientific framework. They contend that the apparent dependence of quantum mechanics on observation may be an artifact of our current theoretical models rather than a fundamental feature of reality. Some propose that the collapse of the wave function occurs due to interactions with the environment, a process known as decoherence, which allows for the emergence of classical behavior without invoking consciousness. Others suggest that the Copenhagen interpretation is merely an interpretive framework, and that future developments in quantum theory may offer a more complete picture that does not rely on the role of the observer. Despite these objections, the idea that consciousness plays a role in shaping reality continues to captivate the imagination of scientists and thinkers. One possible reconciliation of these views comes from the field of panpsychism, a philosophical stance that posits that consciousness is a fundamental and ubiquitous feature of the universe, present in all forms of matter to varying degrees. According to this perspective, even elementary particles possess a rudimentary form of awareness, and the human mind is simply a more complex manifestation of this universal property. If this is true, then the distinction between observer and observed becomes far more nuanced, as every interaction in the cosmos may involve some level of conscious participation. This idea, while radical, offers a compelling framework for understanding the interplay between physics and perception, suggesting that the universe is not merely governed by physical laws but also by an underlying consciousness that permeates all things. Furthermore, the implications of this line of thinking extend beyond the realm of theoretical physics into the domain of cosmology and the philosophy of science. The black hole information paradox, with its unresolved tension between quantum mechanics and general relativity, may ultimately hinge on the role of the observer in determining the fate of information. If the act of observation is essential in preserving the integrity of quantum information, then the universe may be structured in such a way that knowledge and perception are not separate from the physical world, but deeply embedded within it. This perspective resonates with the ancient notion of a cosmos imbued with meaning and purpose, where the act of knowing is as much a part of reality as the forces that govern it. As we grapple with these profound questions, we begin to see that the universe is not a cold, indifferent expanse, but a living, evolving tapestry of interconnected phenomena. The stars that burn in distant galaxies, the black holes that devour matter with inexorable force, and the quantum fluctuations that ripple through the fabric of space-time, all of these elements may be engaged in a grand dialogue with the conscious beings who seek to understand them. In this view, the universe is not merely something to be studied from a distance, but a partner in the act of discovery, revealing its secrets only to those who dare to look. This realization carries with it a sense of responsibility. If consciousness is indeed a fundamental aspect of reality, then the choices we make as observers may have far-reaching consequences. The way we perceive the universe may not only shape our understanding of it, but also influence the very structure of existence itself. This notion, while daunting, is also deeply empowering. It suggests that we are not passive recipients of knowledge, but active participants in the unfolding story of the cosmos. As we continue to probe the mysteries of the universe, we must remain mindful of the role we play in shaping the reality we seek to uncover. Ultimately, the philosophical conundrum of consciousness as the ultimate observer invites us to reconsider our relationship with the universe. It challenges us to move beyond the limitations of traditional scientific inquiry and embrace a more holistic understanding of reality, one that acknowledges the interdependence of the observer and the observed, the conscious and the unconscious, the known and the unknown. In doing so, we open the door to a deeper appreciation of the cosmos, recognizing that the universe may be not only a vast and intricate machine, but also a living, breathing entity that calls out to us across the infinite void. As we venture beyond the enigmatic role of the observer, we arrive at a revolutionary approach to understanding the fundamental nature of reality: loop quantum gravity. This theoretical framework proposes that space-time is not a smooth continuum, as envisioned by Einstein's general relativity, but rather a discrete, granular structure composed of tiny, indivisible units, akin to the atoms of space and time themselves. Unlike string theory, which posits that fundamental particles are vibrations of infinitesimal strings, loop quantum gravity seeks to reconcile quantum mechanics with gravity by redefining the very fabric of spacetime. In this model, space is not infinitely divisible, but instead constructed from a network of loops, mathematical entities known as spin networks, that weave together to form the cosmic tapestry. These loops, which exist at the Planck scale, approximately 10^35 meters, give rise to the three-dimensional space we experience, while their dynamic evolution over time generates the fourth dimension of spacetime. This radical departure from classical physics has profound implications for our understanding of black holes and the information paradox. In the framework of loop quantum gravity, the singularity at the center of a black hole, the point of infinite density predicted by general relativity, is replaced by a region of extremely high but finite curvature. This modification arises from the quantization of spacetime, which prevents the formation of true singularities, and instead leads to a bounce-like behavior, where the collapsing matter rebounds rather than vanishing into an infinitely small point. This bouncing effect suggests that information is not lost within the black hole, but rather transformed and redistributed throughout the fabric of spacetime. Furthermore, the discrete structure of loop quantum gravity implies that the surface area of a black hole, traditionally associated with entropy in the Wittgenstein-Hawking formula, is not a continuous measure, but a countable quantity determined by the number of loops intersecting the event horizon. This insight aligns with the holographic principle, which posits that the information contained within a volume of space can be encoded on its boundary, reinforcing the idea that black holes may serve as repositories of information rather than cosmic voids. The implications of loop quantum gravity extend beyond black holes to the very origin of the universe. In contrast to the Big Bang singularity, where all known physical laws break down, loop quantum gravity suggests a big bounce, a cyclical model in which the universe undergoes endless cycles of contraction and expansion. In this view, the universe did not emerge from a singular point, but rather from a previous cosmic era, where the fabric of spacetime reached a maximum density before rebounding into the expanding universe we observe today. This perspective eliminates the need for an initial singularity and offers a potential resolution to the problem of time's beginning, replacing the notion of an absolute starting point with a continuous evolving process. Moreover, the discrete nature of spacetime in loop quantum gravity may provide a natural explanation for dark energy, the mysterious force driving the accelerated expansion of the universe. If space is composed of quantized units, then the expansion of the universe could be attributed to the creation of new loops, effectively increasing the total number of spatial quanta over time. While loop quantum gravity remains a work in progress, its predictions offer testable avenues for experimental verification. Advances in observational astronomy and gravitational wave detection may soon provide insights into the quantum structure of space-time, allowing scientists to probe the validity of this framework. Additionally, the development of quantum computing and high-energy particle accelerators could enable researchers to simulate the behavior of spin networks and investigate their implications for black hole dynamics. If successful, these efforts could usher in a new era of physics, one in which the fundamental nature of reality is no longer shrouded in mystery, but revealed through the intricate patterns of a quantum cosmos. As we stand on the precipice of this new frontier, we are reminded that the universe continues to unfold its secrets in ways that defy expectation. Loop quantum gravity represents not merely a refinement of our current understanding, but a bold reimagining of the cosmos itself. In this vision, the universe is not a smooth, continuous expanse, but a vast, interwoven lattice of discrete units, each contributing to the grand architecture of existence. As we delve deeper into this framework, we may yet uncover the ultimate nature of reality, one in which space, time, and consciousness converge in an elegant and ever-evolving symphony of quantum possibility. The universe, in its vast expanse, has long been a subject of fascination and inquiry. From the earliest stargazers, who mapped the heavens, to modern physicists probing the fabric of reality itself, humanity has sought to understand the fundamental nature of existence. In the grand sweep of scientific discovery, Few theories have challenged our perception of the cosmos as profoundly as loop quantum gravity, LQG. At its heart, LQG presents a radical departure from classical physics, proposing that the very fabric of spacetime is not a smooth continuum, but a dynamic, woven structure composed of infinitesimal loops. This revolutionary idea suggests that space and time are not infinitely divisible, but instead composed of discrete, quantum units, grains of spacetime, that shimmer at the smallest scales. Such a notion upends centuries of thought, from Newton's absolute space to Einstein's elegant curvature of spacetime, and introduces a vision of reality where the cosmos is stitched together by an intricate network of quantum threads. At the foundation of LQG lies the recognition that our current understanding of physics breaks down at the most extreme conditions, particularly near the singularity of a black hole. General relativity, which describes gravity as the warping of spacetime, predicts that matter collapsing into a black hole compresses into an infinitely dense point, a singularity where the laws of physics cease to function. However, quantum mechanics suggests that such infinities cannot exist in nature. Loop quantum gravity seeks to reconcile these two pillars of modern physics by offering a framework in which spacetime itself is quantized, eliminating the possibility of singularities altogether. Instead of collapsing into an endless void, matter reaches a boundary defined by the smallest possible length, the Planck scale, where the fabric of reality resists further compression. This fundamental graininess of spacetime could mean that black holes do not end in oblivion, but instead transform into new realms of existence, preserving information rather than destroying it. The implications of this theory extend far beyond the event horizon of a black hole. If LQG is correct, the universe is not a passive backdrop against which events unfold, but an active, evolving structure composed of interwoven quantum threads. This perspective shifts our understanding of time and space from a continuous flow to a sequence of discrete, interconnected moments. Moreover, it offers a tantalizing solution to one of the greatest enigmas in modern physics, the black hole information paradox. If information truly cannot be lost, as quantum mechanics dictates, then the fate of matter falling into a black hole is not annihilation but transformation. In the framework of LQG, the universe becomes a vast, ever-renewing tapestry, one where every thread carries the imprints of what came before, and every collapse gives rise to new beginnings. To grasp the essence of loop quantum gravity, one must first abandon the familiar notion of a smooth, continuous spacetime and embrace the idea that the universe is built from discrete, quantized building blocks. Unlike the classical view, where space and time can be divided indefinitely, LQG proposes that at the smallest possible scale, the Planck length of approximately 1.6 10⁻35 meters, spacetime is no longer a fluid continuum, but a mosaic of indivisible units. These units manifest as a complex network of loops, entangled in a web-like structure that constitutes the very foundation of reality. This intricate lattice, often referred to as a spin network, is not static but dynamic, constantly shifting and evolving according to quantum mechanical principles. Just as atoms form molecules through chemical bonds, these loops intertwine and interact, weaving the fabric of space and time into a coherent whole. At the heart of LQG lies the mathematical framework of spin networks, graph-like structures composed of nodes connected by edges, each representing quanta of space. These nodes correspond to elementary volumes of space, while the edges signify the connections between them, forming a three-dimensional lattice that defines the geometry of the universe. When extended over time, these spin networks evolve into spin foams, which describe the quantum fluctuations of space-time itself. In this picture, space is not a fixed entity but a dynamic configuration of quantum states, continuously shifting as loops merge, split, and reform. This granular structure means that space is not infinitely divisible. Instead, it has a minimal unit of measurement, preventing the formation of singularities where density and curvature become infinite. This radical departure from classical physics has profound implications for our understanding of black holes. According to general relativity, the gravitational pull of a massive object can become so intense that not even light can escape, leading to the formation of a singularity, an infinitely dense point where the known laws of physics break down. However, within the framework of LQG, the discrete nature of spacetime imposes a fundamental limit on how tightly matter can be compressed. As a star collapses under its own gravity, the loops of quantum spacetime resist further contraction, reaching a critical threshold where the repulsive effects of quantum geometry counteract the force of gravity. This leads to a phenomenon known as the Planck scale bounce, where the collapsing mass rebounds instead of collapsing into a singularity. Rather than vanishing into nothingness, the matter is transformed, potentially emerging in a different region of spacetime, or even birthing a new universe. The Planck scale bounce is not merely a theoretical speculation, but a consequence of the mathematical consistency of LQG. By applying quantum principles to gravity, researchers such as Carlo Rovelli and Lee Smolin have shown that the universe may avoid singularities entirely, replacing them with a cyclical process of expansion and contraction. In this model, the Big Bang is not the beginning of time, but rather the result of a previous cosmic collapse, with the universe undergoing an endless sequence of cycles. This idea challenges the conventional view of the universe as a singular, linear progression, and suggests instead a dynamic, self-sustaining system, where information is preserved across cosmic epoch. Moreover, the implications of LQG extend beyond cosmological models and into the nature of reality itself. If spacetime is fundamentally discrete, then the universe operates less like a continuous film and more like a series of still frames, each one a snapshot of a quantum state. This perspective raises profound philosophical questions about the nature of time, causality, and the emergence of macroscopic reality from quantum foundations. It also provides a potential resolution to the black hole information paradox, a long-standing conundrum concerning whether information is truly lost in the event horizon or somehow preserved. In the framework of LQG, the Planck scale bounce ensures that no information is destroyed, instead transforming it into a new configuration as the black hole evolves. By reimagining the fabric of spacetime as a granular, quantum-structured entity, loop quantum gravity offers a compelling alternative to the classical view of the universe. It challenges our deepest assumptions about the nature of reality, replacing the smooth, continuous fabric of Einsteinian spacetime with a vibrant, interwoven tapestry of quantum threads. In doing so, it opens the door to a new era of physics, one where the universe is not a passive stage for cosmic events, but an active, evolving structure governed by the fundamental principles of quantum gravity. If loop quantum gravity is correct, then the universe is not a linear progression of events, but an intricate, self-sustaining cycle of creation and rebirth. Black holes, once considered the ultimate endpoints of cosmic evolution, become instead the gateways through which information is not lost but transformed, carried across the fabric of reality, into new domains of existence. This perspective reshapes our understanding of the cosmos, suggesting that the universe is not a singular entity, but a vast interconnected web of quantum states, each influencing the next in an unbroken chain of transformation. The implications of this view are staggering, challenging the conventional notion of entropy and offering a glimpse into a universe that may be both finite and infinite, boundless yet cyclical. One of the most profound consequences of LQG's framework is the idea that information is never truly erased from the cosmos. In classical physics, the concept of entropy suggests that information tends toward disorder and eventual loss. However, quantum mechanics asserts that information must be conserved, leading to the long-standing black hole information paradox. If a black hole swallows matter, where does the information contained within that matter go? Does it vanish into oblivion, violating the fundamental laws of physics? Or is it somehow preserved, awaiting a moment of revelation? LQG offers a compelling answer. Rather than being destroyed, the information encoded in matter is woven into the very fabric of spacetime, carried through the Planck scale bounce and emerging in a new configuration. This means that the universe, in all its complexity, is not a closed system, but an open, self-referential loop, where every act of destruction is followed by renewal. This cyclical nature of the cosmos extends beyond the event horizon of a black hole and into the grand structure of the universe itself. In the standard model of cosmology, the Big Bang represents the origin of everything, time, space, and matter. But within the framework of LQG, the Big Bang is not the beginning, but rather the latest iteration of an ongoing cosmic cycle. Just as a black hole reaches the Planck scale bounce and rebounds into a new phase of existence, the universe as a whole may undergo similar transformations, expanding and contracting in an eternal rhythm. This idea, known as the cyclic universe model, suggests that the cosmos has no true beginning or end, but instead exists in an unbroken sequence of cosmic epochs, each shaped by the remnants of the last. The universe is thus not a singular entity but a continuum of possibilities, where every collapse gives rise to new forms of order and complexity. This perspective carries profound implications for our understanding of time and causality. In classical physics, time is treated as a continuous linear dimension, flowing inexorably forward from past to future. However, within the framework of LQG, time is not an independent entity, but an emergent property of quantum interactions. Just as the ticking of a clock is a macroscopic manifestation of atomic oscillations, time itself arises from the interplay of quantum states within the fabric of space-time. This means that the distinction between past, present, and future is not as rigid as traditionally assumed. Instead, the universe may operate on a principle of self-reference, where the future influences the past and the past shapes the future in an intricate feedback loop. Such a model challenges our intuitive understanding of cause and effect, suggesting that the universe may be more akin to a vast recursive computation than a simple progression of events. Moreover, the idea that information is preserved and transformed across cosmic cycles raises intriguing questions about the nature of consciousness and existence. If the universe is a self-sustaining system, where every bit of information is encoded and carried forward into new configurations, then the very essence of reality may be a form of cosmic memory. In this view, the universe is not a collection of isolated entities, but a vast interconnected whole, where every action leaves an imprint that reverberates through time. This notion resonates with ancient philosophies that speak of an eternal recurrence, a universe that endlessly repeats its patterns in an unending cycle of creation and dissolution. Whether or not such a model is ultimately proven true, it offers a compelling vision of reality, one in which existence is not confined to a single lifetime or a single cosmic epoch, but is instead part of an infinite unfolding process of transformation. In embracing loop quantum gravity, we are invited to see the universe not as a static, deterministic machine, but as a living, evolving entity. The fabric of space-time is not a passive backdrop, but an active participant in the dance of existence, shaping and being shaped by the interactions of matter and energy. The Planck scale bounce, the conservation of information, and the cyclical nature of the cosmos all point to a universe that is not only vast, but also deeply interconnected. Every black hole, every galaxy, every particle is part of a grand, interwoven pattern, where nothing is truly lost and everything is in a constant state of becoming. This vision of reality, rooted in the principles of quantum gravity, challenges us to reconsider our place in the cosmos, not as isolated observers, but as integral components of an ever-unfolding, self-referential tapestry. As we stand at the threshold of comprehension, the cosmos reveals itself not as a fixed construct, but as an ever-evolving narrative, woven from the finest threads of quantum gravity. Loop quantum gravity has illuminated a path where the universe is not a passive stage for cosmic events, but an active, self-sustaining entity, pulsing with the rhythms of transformation. In this grand design, black holes are not mere abysses of oblivion, but conduits of renewal, carrying the imprints of the past into the unknown. The Planck scale bounce, the conservation of information, and the cyclical nature of existence all suggest a universe that is not linear in time, but recursive in its essence, a self-referential loop where every collapse gives rise to new beginnings. Yet for all the revelations that LQG offers, it is but one thread in the vast tapestry of cosmic mystery. The horizon of knowledge stretches beyond this single framework, beckoning us toward deeper inquiries and broader perspectives. The black hole information paradox, once a riddle of entropy and erasure, now stands as a doorway to a more profound understanding of reality. If information is indeed preserved across cosmic cycles, then the universe is not a closed system but an open, self-referential entity, where the past informs the future, and the future echoes the past. This insight compels us to look beyond the immediate confines of our observable universe and consider the possibility of a greater cosmic architecture, one where the boundaries between distinct realms blur and the fabric of reality extends into dimensions beyond our current comprehension. The paradox is not merely an enigma of theoretical physics. It is a gateway to a deeper truth, one that may reshape our understanding of existence itself. And so, as we trace the intricate weave of quantum gravity, we find ourselves poised at the edge of another great leap in understanding. The universe, in all its complexity, is a vast interconnected web of possibilities, where every law of physics, every cosmic event, and every quantum fluctuation contributes to the grand design. In the next chapter of our exploration, we turn our gaze beyond the singularities of black holes and the granular fabric of space-time, venturing into the realm of the multiverse. Could our universe be but one of many, each born from the remnants of a cosmic collapse, each unfolding in its own unique expression of time and space? The answers lie ahead, waiting to be unraveled by those who dare to dream beyond the known.